Hello, hi everyone. My name is Rafał Motriuk. I'm a science and technology journalist and I'll be your host today. Thank you very much for having me. Our event is called Code Dive. So we are back for another Nokia's Code Dive conference this year, and I know so many of us enjoyed those previous years, but you might enjoy this year's even more because, well, let's face it, it's the most technologically advanced. So the way we're doing it this year is we're doing it as live, which means we make it appear as if it was live, but in fact, we have recorded everything in advance. By the way, we're broadcasting from Wrocław, a Nokia hub here in Poland. And with that, I'd like to give floor to Taras Lukaniuk, who's head of Nokia's Wrocław Technology Center. Taras, over to you.
Thank you, Rafał. 7 editions, 250 plus speakers, 40,000 participants, and first time online. The unfortunate reason we cannot meet in our usual cinema rooms is obviously COVID. That's the reason we are doing it exclusively online this year. When the pandemic has started, we asked ourselves, will we manage? And this number proves to me that at the bottom of our heart, we all are code divers. We do explore opportunities when others see a problem. We all enjoy learning. When the problem is solved, we feel satisfied for the next couple of minutes, and what do we do next? Next, we are looking for another challenge to pick up. So what is Code Dive? Code Dive is more than just a conference. It is a tradition. Like the fact that festive season comes every December, it is a fact we all meet at a Code Dive every November. Many of you are with us since the first edition, starting from 2014. But we also do have many new participants. For the first-timers, Code Dive is an event where IT professionals meet, discuss the latest trend, share their ideas, and share their experience. We also would like to have a platform for networking. I'm a fan of simplicity, as you can see, and I would like to make it very simple, using the comparison operator. Nokia Wrocław equals Code Dive. Code Dive equals Nokia Wrocław. And from here, Nokia Wrocław side, I would like to thank you all, participants, speakers, media, and organizers, for making this happen. So relax in your chairs, put your headset on, and enjoy the learning with us. Thank you, Rafał.
Thank you, Taras. Thank you so much for this warm welcome. So this year we've got 2 streams, A and B. So take your pick, choose the one you like, and, well, let's get started. So our first speaker today is Felix Petriconi. Now Felix has been employed as a programmer since 1993. He started his career as a freelance programmer in telecommunication and automotive projects, and since 2003 he's been employed as a programmer and development manager at Mewis Medical Solutions in Bremen, Germany. He's part of the team that develops and maintains radiological medical devices. His focus is on C++ development and application performance tuning. He's a regular speaker at the C++ user group in Bremen, a blog editor at isocpp.org, a contributor to the stlab.cc concurrency library, and chair of the ACCU conference. So, concurrent code, test it, but how? Felix, the virtual floor is yours.
Rafał, many thanks for this nice introduction. Welcome to my session about testing of concurrent code. Many thanks go to the organizers who invited me again to speak on this conference. It's a pleasure to speak here, even that I cannot be in Wrocław. as I was already introduced so nicely, there's no need to spend more time on me. So, let's have a look on the software development cycle. The complete cycle covers many different aspects. Everything starts with the product vision. So somebody has an idea of what might be useful. And then this idea is brought to the marketing, and they see if there are people who really would like to buy this product. If this is the case, then we start with the requirements. And we start with coding, testing, later the deployment of the software, and later on, and then in the end, the maintenance. Today, I want to focus a little bit, I want to speak a little bit of requirements and then about a very special part of testing. Very seldom requirements specifically talk about concurrency. Most of the time they talk about features, about a certain part of performance. But clear requirements are the very most important part from my point of view. It's a joy to implement well-defined requirements, and it's very easy to derive good test cases from them. I recommend that you insist on getting a story in prose. What the user actually wants to achieve when you don't have the possibility to speak directly with the customer. So what I mean is that you get context information about what the user wants to do or what he needs. Not only there's a button and this should do this or that. Without the context, it's very hard to really know what is the best would help the user. And from these user stories, you can derive your use cases and in the end your requirements. So let's now talk about testing. Some parts that I'm talking about are not specific to concurrent code. I will talk about different aspects that you should take into account while you do your tests. In the very end, I give you a very special case study of code that I've developed some time ago. All my code examples will contain C++ code, but most of the ideas can be transferred to other languages as well. When we talk about testing, very often the testing parameter is taken as an example of how the test should be structured. This test automation parameter was described by Mike Cohn in his book and by Lisa Crispin and Janet Gregory in their book. What does this parameter want to visualize? It says that the majority of tests should be unit tests and that the number of tests should decrease as more as one looks at the upper levels. So most of the test cases should be unit tests, then on the service level should be less tests, and the UI should just have very few tests. But is this really true? I have not found any scientific proof that this distribution leads to better software. On the contrary, we in our company and others experienced that most errors and regressions are not within the single units, but between them. And Jim Compline has written some years ago a very instructive paper on this. It's called Why Most Unit Testing is Waste, and a follow-up on this. I give you a link at the end of the presentation. We in our company made the best experiments in testing from end to end through an interface just below the UI. When the test suite took too long, which is the major reason that this testing automation pyramid is sponsored, or which they say this should be done, that testing through the UI takes too long. This might be, but it's very easy, or what we did, we put more hardware to the test setup and run the tests in parallel. And we found race conditions because of the extreme fast test execution of our application. And these race conditions would have never been found in manual tests or within unit tests. And on top of this, creating a realistic mock in an asynchronous environment is very difficult from my point of view. Especially if the mocks should keep up to date in sync with the real system. This can be very tedious and it's very easily overseen. So what I mean, when you have a mock-up of your of the environment of the code that you want to test, then this mock, then this mock should behave exactly as the real system. But the first thing is, how could you prove that this is really the case? And does everybody who changed the system really thinks about changing this mock as well? Another one who talks about this is Peter Summerlad in his session from ACCU 2018 with the name Mocking Frameworks Considered Harmful. I really can recommend to look into this. So, what kind of tests should be used on which level? So, I recommend that you use use cases on algorithms and code where you have an independent oracle. Use such tests as well for generic code or STL-like code, so for instance for containers and algorithms. And use integration and system tests, especially for business logic. In my further discussion, I will talk only about unit tests. So let's have a look into the unit test strategy. Design your algorithms, so the thing that you want to test, in a way that it allows decomposition into smaller parts. Then it's much easier to test these smaller parts in a serial way. Then design your algorithms such as that they don't need locks. I mean mutexes for commonly used data. If your algorithm needs to write to shared data because it's unavoidable, then try to pre-allocate and reserve it for each current task at a specific region. Let's have a look as an example. So this is an example from our code. We had the problem that we have huge images that needs to be decompressed into so that they can be transferred faster over the socket. So what we did, we sliced the complete image into different stripes. In each of these stripes is then compressed on its own on a single core. Now I just have visualized here 4 stripes, but in the end we divided the complete image in 16 stripes because most of the hardware has 16 or more cores available. And then we pre-allocated the memory where the compressed image should be stored. Of course, this is then a much smaller area. And then we could do the complete compression without using any mutex. So mutexes, as you all should know, is the best. Using a mutex is the best way to slow down your application. I recommend here to look into a session by Sean Parent where he says that you shouldn't use synchronization primitives like mutex, atomics, and all this stuff. What are the problems that your code can have? So the first are race conditions. So what are race conditions? When you have unsynchronized read and write operations on the same object from different threads. Deadlocks can happen. For instance, if you have dependency of parallel tasks on other tasks, or the system goes out of resources. What do I mean with this? For instance, you have a thread pool where you can have 4 tasks in parallel. And all these tasks wait on a certain condition. Then this condition can be fulfilled when the 5th task gets executed. But this 5th task is put into the queue behind all the 4 waiting tasks. And so this 5th task cannot be executed, and so all 4 tasks wait there forever. Another point is correctness. If you are working in concurrency, it's very easy that you start working on objects that were not yet constructed or that were already destroyed. That the same is true if you pass references to objects into a thread, and the original object leaves the scope, but the thread still tries to access to it. And finally, the reason why you do all this concurrent work is efficiency. So you want that your task get executed as fast as possible. So here are the aspects of fault sharing, locking, memory I/O, and code versus host data comes into account. I do not want to go into the further details of these individual aspects. There are many other talks about this. So, what is that problem for tests? Normally, concurrent code is often highly optimized. That's the reason that I use concurrency from the beginning. This results often that there are fewer level of abstractions, so that you have less access points to test. So when you come to a test setup, there are different ways to test it. So I recommend that you set up your system or your test in a way that not only, for instance, all the time 4 tasks are executed in parallel to get finished, but that you change this from 1 to n instance of this task to run in parallel. And do the same for the setup of your cores. Because not all systems will have the same number of cores. There might be systems that just have one single core or 2 cores. And this because if you just have one core, it's very easy that you run into deadlock again. Because one task is waiting for the result of another one, but this other one does not get fulfilled because it's stuck behind the first one. So, if you have generic code, you should consider that you write your tests, for instance, for void types, then for copyable types like primitives, int or string, and for objects of custom size. This can have a huge influence in the execution of your test, because the optimizers work differently of these different kind of objects. If it's part of the use case of this library, for instance, then you should take of non-copyable tasks into account as well. So, when you set up now your task within the test, one strategy is to bring all tasks into a starting position, and when they are all ready to run, then trigger them, for instance, with a latch or by signaling of a condition variable, and let them run in parallel until then the test and the result is there. Another setup is if the test, that the task should be not all run at exactly the same time, but with a slight shift between them. So you trigger them and then they run a little bit different. And then you can do this in another way, that you start the task with random delay. All this is necessary to ensure that there is no dependency within your code, or if there's a dependency, that this doesn't have an influence on correctness. When you come to the test execution, there are different aspects or different ways to approach the problem. So, your system can be under stress. So many things are going on your system. This can be either your application that does something else at the same time, or that different applications cause load on your application. This is something that you should take into account, because this might influence your subject under test. Another approach is that you do a brute force. So you run the test for a very long time, for many hours. Or that you run several instances of the same test for a long time, and see if there, in any kind of these tests an error happens. Then it is important if your software might run on different architectures. For instance, most common architectures are today ARM and x86 CPUs. I'm pointing out this because the low synchronization primitives like atomics behave slightly different on these architectures, and this so your code might work on one architecture, but it fails on a different one. And very important. Not only the processor architecture is important, different CPU generations and operating system can have an influence as well. For instance, we once had a problem that a certain CPU feature was not made available by the operating system, even that the CPU supported it. So we had highly optimized code which just checked for the CPU ID. And then the code decided, well, this means that the certain CPU instruction should be available, and then the code used it. But as you remember, the operating system did not enable this feature, and in the end, the result that the application crashed or was aborted because of an illegal instruction. There are certain tools that support you in checking the correctness of your code. For instance, there is TLA+. This is a system where you describe in a special language the problem that you want to solve. And then a solver is running on these equations and sees if there are problems in your code. And the system, even that I personally did not use it, I know that other companies use it for their code or for their even for their hardware development. Then there are tools like the thread and address sanitizers, which are available today in Clang, GCC, and Visual Studio. So they check for race conditions and similar in your code while you executed it. Another very helpful tool are is when you have pre and suffix allocated memory. That means that a certain pattern is written in every memory block that you allocate before and after the memory block. And whenever the memory block is then released, so you call a destructor on it, then the system checks if these patterns are still correct. For instance, if your code writes too far, then this pattern would be overwritten, and this is of course the bug. Some environments support this in a debug environment, but unfortunately not in a release build. And if you want to do this in a release build, you can write such an allocator by yourself. Andrei Alexandrescu has sketched an allocator implementation in 2015 at the CPPCon. And this design allows you to implement a guarded allocated deallocator by yourself. I did this by myself, and it's not very complicated. Then there is freely available the internal parallel suite, which has a thread analyzer as well. And of course there's the Vagrant suite, which have a bunch of tools, which provide you a bunch of tools to ensure that your code is correct. Besides the correctness, performance is another important topic. So you can do your performance measurements with simple measurements like with chrono, which goes from minutes to nanoseconds depending on your platform. Then you can use Google Benchmark, which is a very sophisticated library that allows you to write code or write tests to see how good your code performs. Or you can use performance coder directly on the CPU. And something that I found very useful is that you knew if you are working with generic code, that you use annotated types. to check your code. What I mean with annotated types. This is a type that counts internally whenever it was instantiated, copied, moved, and so on. So in the end, when you have a certain idea of how often your object should be copied within your code, then you can use it with this annotated type and see at the end if it was really copied as often as you think, or much more often. Or if you think that your object should never be copied within your complete algorithm, but just moved, then you can look in the end, is this really true? Was there really no copy or assignment of this object, but just moves? I found this very useful, and the implementation is very easy. And if you don't want to implement it by your own or on your own, then you can look into our SDLab library. There we have an annotated type. So now let's look into my case study. Within our library, I had the problem that I wanted to implement a prioritized thread pool. What is the thread pool? The thread pool is a device that uses, depending on your configuration, as many cores as your system has available. So for instance, if your system has 4 cores available, and then you want to utilize these cores as much as possible, then all tasks should be spread on these individual cores in the best manner, so that there's at least idle CPUs available. So all these cores, all these thread pools take a void function, or for instance a lambda, as a task. So what is this prioritized thread pool? It may be that there are tasks in your application which should be executed with a higher priority than other ones. So most of the systems offer 3 different priorities: low, medium, and high. So medium is the other one for default. And that means that if you send a high priority task and a medium priority task to your thread pool, and many of them at the same time, then all high priority tasks should be executed before the low or the lower task with the lower priority. So let's have a look at how this would look like. So we have a task which does some computation, and then we just, here as an illustration, we pass this to a low executor. This is the executor that uses, or if you pass this task to a low executor, then this task is a task with a low priority. If you use the medium executor or default executor, then this is a task with the medium priority. And if you pass this task to the high executor, then it gets the highest priority. Let's have a look how this would like in a simulation. So we start with one high priority and one medium priority task. And then they are executed. First we take the high priority task and then low execute. Then the next high one is taken before the medium ones. And then all the medium priority tasks are executed. And the low priority task has to wait until all medium and high priority tasks were executed. I had two reference implementations. One was on Mac OS, called Grand Central Dispatch, and on Windows, the Windows Thread Pool. And my goal was that they should be as close as possible to, as the one that's available on the platform. So it should be, of course, correct, and it should be as fast as possible. So when we talk about tests, there are two different kinds of tests then necessary. The first is, of course, correctness. That means that all tasks submitted with different priority should be, of course, executed. As well, for instance, if the queue went dry and you put new task into them, then they should be executed as well. And the high priority task should always be executed before the one with the lower priority. And you have to test as well the instantiation of the thread pool as well as the destruction of the thread pool. So or in other words, you have to take care that it works correctly. So how do you deal with tasks that are still on the thread pool? And of course, we should look that, we should see that this thread pool has the highest possible throughput. So, one problem while implementing the test cases was there was no interface to access these individual priority queues. So there was no function that would give me access to these priority queues. And this is because this thread pool was highly optimized for best performance. So my approach was, in this case, to test with the probability of how many tasks were picked correctly. So now let's have a look into a little bit of code. At the beginning, I have a bunch of variables, of atomic variables, and these represent the number of tasks with high priority, with medium priority, and with low priority. Oh, sorry, that was my mistake. So, forgive me this, but I'm working on two different applications at the same time. So, and then there is a variable which counts the tasks that were already done. And for checking this correct execution, I have a special check task, which has a template parameter with the executor priority. So that's medium, high, and low. I will go into further detail a little bit later. So, when we look into the test case, I run this test case with 1 million iterations. That's just random high number. Then I'm interested in the number of correct low and medium high executions. What do I mean this with correct execution? With correct low execution, or an instance of a correct low execution would be if at the same time no medium and no high task was available in the thread pool. And then I set up the tasks. In this example, I start all tasks from the main loop, so from the main loop of this task. And in the first line of the loop, I pass a task to the low executor. So this is a task with a low execution priority. And I pass by reference the correct low and the low count. So the correct low is, as I defined earlier, the number of correct low low tasks at the correct time point. Then I pass, or then I create a task with the high priority and pass this to the high executor. And then I create a task with the medium priority and pass this to the medium executor. And I'll do all this 1 million times. So this is now the setup for my test. And then I just have to wait until all my tasks were executed. And I don't do a busy waiting, but I do a rest, which is internally a wait for 1 millisecond, and then a wake up of this code, and then check again if all the tasks were executed. And in the end, I print the correct percentage of correct medium and correct low executed task. So let's have a look into this check task. This check task has the priority as a template parameter. And it has two reference members, one to the correct scheduled count and one to the current priority count. To the current priority count, I'm sorry. And these are passed with a constructor. So, for instance, when I instantiate this class with the medium priority, then the medium priority count will be increased by 1 because now we have one of this task living in our system. And I do this for all the different priorities, depending on the parameters that I pass by reference to the constructor. So, then this task has a function called operator, because this is the function which is then executed on the thread pool. At the very beginning, I decrement the current prior count. That means that now I have one task less with this certain priority in the system available. Why I'm doing this? Because I have no direct access to the queues which are in the thread pool. So I'm counting outside how many tasks I'm sending to the thread pool for the different priorities. And then there's a const if statement. So this is just executed and just taking into account if this instance of the class was with the priority of low or medium. And what do I count within this expression? So I see it that this task was executed at the correct time when the number of high priority tasks plus the number of medium priority tasks was equal to 0. Then there was no task available or running. There was no task in the system waiting with a higher priority than low. And then this was executed at the correct time. if this check task was instantiated with medium priority, I do nearly the same. I check, was there any task with a priority high in the system? Then this was executed too early. Or in other words, if the number of tasks with the priority high was equal to 0, then this was executed at the correct time point, and I count this in this correct schedule count. And in the end, this task was done, and this is one of the 3 million tasks that I'm executing in this test. I'm aware of the fact that this is not absolutely correct, but I didn't see any possibility else to check that the tasks were executed in the correct order. So let's have a look at some measurements that I did. All these tests were executed on my MacBook Pro from 2015, which has, I think, 6 cores and 6 GB RAM. And the tests on the Windows system were on a system with an AMD Threadripper with 12 cores or 24 hyper-threaded cores. And the system has 32 GB RAM. So let's have a look at the different tests that I did. In this first column, in this first 3 column, there are the results of the test that I just have shown you, or the code that I have shown you. So this is just the minimal task of execution, just the check that the tests were executed at the correct time point. So then I wrote another test, which I have not shown here, but what you can find online, when there was some kind of calculation done within the task. In this case, I calculated the Fibonacci number of 10,000. And all these tasks were put into the thread pool from within the main loop. And in the end, I did a third test where the task was not inserted from the main loop, but the task, one task which was executed on the thread pool spawn a new task again on the thread pool. Again, I did this with the load of calculation. Then in the first bigger row, these are the results which were done on the MacBook. So the top row, that were the results with the lib dispatch. So this is the thread pool that comes from macOS, and STLab is my own implementation running on a Mac. And then I did the same task on the Windows thread pool and on Windows with my own implementation. So I just will now point to certain aspects that I've seen. I will not discuss the results in further detail. One can spend a lot of time in trying to figuring out what's going on the system, and probably the tests have to improve as well. So the first thing is the timing. Even that the Mac is much older and has much fewer cores than the Windows machine, the tasks were executed, or all tasks were executed in much fewer time than on the Windows machine. My assumption is that the setup of the system has here a bigger influence, because within the thread pools is a queue for the elements, for in the individual tasks. And my assumption is that increasing this queue for newer elements takes on Windows much more time than on Mac, so that the memory handler inside Windows is not as fast as the memory handler on the Mac. Another interesting point is the timing and the end. So of course, everything needs much more time now, but the difference between the Windows system and the Mac system is, from my point of view, enormous. And I have to go into further investigation what is going on here. So, but I do not want to spend too much time on analyzing this table. The other interesting point is that there are on the Mac and on Windows in the middle column, that there are areas where 0% of the tasks were executed at the correct time point. So that means that there were tasks with a lower priority were executed, even that there were tasks with a higher priority. So far, the only reason I can see for this is that these tasking systems on Windows, on Mac, do much more than taking care of the individual tasks. But they take care about other aspects as well. So for instance, the implementation of our thread pool just have as many threads running as there are cores available. So if you have 4 cores, then it will just spawn 4 threads on these 4 cores. And when the tasks are waiting on a mutex or on another event, that can happen that all 4 tasks on these 4 threads are stopping and waiting on another event to finish. The systems from Windows and from Mac normally spawn, in this case, another thread, because they have access to the kernel and see that none of the other 4 tasks make any progress. So in this case, they spawn a new thread so that there's a chance that this new task then gets executed. Since I don't have access to the kernel to see if, or to ensure that all tasks make progress, our thread pool is much simpler from this point of view. And this leads to the fact that perhaps the correct priority of execution is not that accurate as it is in our implementation. So let's come to a conclusion at the end. Again, I can not point it out. It is very important that you develop together with your product owner or your product manager good requirements. Good requirements are the key factor for success of your code. Then structure your algorithm as much as possible into serial parts, because they are much easier to test. If you have to test codes that run in parallel, try to influence within the test the kind of the parallel execution. So let one part start let one part start a little bit earlier than the other one, and try to figure out if he has any problem on your side or in your code. Then use threat analyzing tools. That helps enormous to find even very, very subtle bugs. So, in the end, there just can to say thank you to certain ones. For, of course, my family, which supports me while I'm working on this concurrency library. Then John Parent, who taught me over time lots about concurrency and especially about abstraction. And all contributors to the STLab library. Not only to those who submitted pull requests, so as well to those who support, who sent us bug reports. All this makes the library better and better over time. So in the end, there's a small reference, as I've promised, about certain talks or books that I recommend or papers that I recommend to read. And if you want to know more, don't hesitate to send me an email or reach me on Twitter. I'm happy to help you on your problems. Thank you very much.
Concurrent code, Felix, Petriconi. Felix, lovely. Thank you very much for your wonderful presentation. You're watching Code Dive. Don't go away. We'll be back shortly. Welcome back. Our next speaker is Iulia Știrb, and she graduated from the Politehnica University of Timișoara in Romania with a master's degree in software engineering. During his studies, she contributed to publications by the well-known Elsevier Publishing. Her focus was on compilers, optimizing for energy consumption, and on image processing. She is an associate teaching assistant at the Politehnica University of Timișoara in Romania. She gives classes on databases, programming languages, programming techniques, and formal languages and compiling techniques. Currently, she's studying for a PhD in computer science. Outside of work, she likes to read and count her blessings, so she's really thankful for this conference, and she's really grateful to all the good scientists she's recently met. So, Iulia, take it away.
Hello everyone, my work is entitled Getting Customized Runtime Hardware Details at Compile Time for Thread Mapping on Any Machine. My name is Iulia Știrb, and this is the content of the presentation that mainly focuses on getting the number of logical cores and physical cores of the underlying machine using the information at compile time and using it in a mapping algorithm. So to do that, I have identified two methods. I will end with a comparison between the two methods and with the conclusions. In Linux, the number of logical cores and the number of physical cores can be obtained by reading the CPU info file, which is a file that is written at system startup. To get the number of logical cores, we would need to search for a line that starts with processor keyword in the CPU info file, and to get the third element after the keyword processor that is separated by spaces. And to get the number of physical cores, we will need again to read the CPU info file and search for a line that starts with CPU keyword and get the fourth element after the CPU keyword. To be able to get the information that the command returns in a C program, we have the system function call, which executes a command given as a parameter and returns the result of the command. The number of logical cores and physical cores can be input to thread mapping algorithms, such as NumABTM in reference 1, which maps threads to cores depending on thread type and on the underlying architecture. So how is mapping done depending on the thread type? Well, threads need to be first classified depending on the degree of communication with other threads according to reference 1. Threads without data dependencies with others can be mapped uniformly to processing units. Threads that have fewer dependencies with others can be mapped to less loaded processing units, according to reference 2. The number of logical cores per CPU is used in mapping data sharing threads, which are threads that can share data with any other. Those threads are mapped close to each other in the memory node to fetch data from a common cache, according to reference 3. Once having the number of logical cores and the number of physical cores, the number of logical cores per CPU can be obtained by dividing the two. In this scope, CPU term can be associated with a memory node, with a core or multiple cores attached in the context of non-uniform memory access systems, NUMA systems. The number of logical cores per CPU represents the number of logical cores, usually a power of 2, in the memory node, again in the context of non-uniform memory access systems, NUMA systems. Before starting the main topics of the presentation, I made a short intro on which native code and bytecode mean. So native code is compiled to run for a particular processor and its set of instructions, or could be adapted to a different processor by an emulator, and the software would run slower in emulated mode. Native code or bytecode or interpreted code, on the other hand, runs in a virtual machine such as Java Virtual Machine, JVM. The VM converts the no-platform-specific code into native code that runs in a specific processor. So native code is particular to a processor, while bytecode is no-platform-specific code. There are two ways mapping can be done depending on hardware architecture details. First method that I have identified concerns using a JIT compiler, just-in-time compiler, for the mapping to be done before running the application. Then the second method concerns executing the mapping algorithm at the start of the application runtime by including the intermediate representation of the mapping algorithm in the beginning of the intermediate representation of the application. So before moving to method 1, using a JIT for executing a thread mapping algorithm based on hardware architecture details, I made a short intro on how JIT compilers work. So JIT compilers provide compilation during the execution by generating IR, which is passed to the middle end, which is the optimization phase, and then to the backend, which is the code generation phase of the compiler, and the scope is native code generation. I made several case studies. The first is on Microsoft.NET products and how they use JIT. So Microsoft.NET compilers produce bytecode, so-called Microsoft's intermediate language. The MSIR can be compiled into native code before execution by a JIT for faster performance. So I have identified two possible scenarios that can slow the execution. The scenarios concern having native code for processor P1 and wanting to execute it on processor P2. So we start in the first scenario from intermediate representation, then by compiling we generate native code for processor P1. Then we emulate the code to be able to run the native code for processor P2. The second scenario starts again from intermediate representation. Then I generate native code for processor P1, then dispatch that code and get back to LLVM IR. And then by compiling, I generate native code for processor P2. Both those scenarios are time-consuming, especially the first one. So we don't want to get into the emulator stuff, which is slower. So there is a solution to the scenarios that were last mentioned. The solution concerns bytecode. So we start from bytecode, then we get the bytecode into execution. But just before the application starts executing, a JIT compiler is called. We get the native code for the application, and then we resume the execution of the application from its beginning once having the native code of it generated. And this is much more faster than the first two scenarios, which usually slow the execution. Another case study on using JIT is on LLVM products. So LLVM is a compiler entitled Low-Level Virtual Machine, which can be used to construct JIT. To do that, you need to get the LLVM IR code of the application into memory. Then you would use the LLVM library to generate native code in memory, which gives you back a pointer to the JIT that you can call anytime afterwards. Other approaches, such as the one in 4, uses JIT to retarget the executable code, extracting fragments from an interpreter written in C and compiled to executable code, and using the fragments in a native compiler, which patches those with others like jump target addresses. Without JIT, the interpreter would have had to be dispatched, and the interpreter code would have needed to be accessed for adding another target, while recompiling would have taken time as well. So moving on to the first use case of using a JIT compiler, that is to use the JIT to retarget a function execution to the underlying machine. For example, you want to run a function with parameters of different storage sizes depending on the compiler used. So if the function is compiled using another compiler, let's say, then using LLVM JIT to retarget the function to the underlying machine may cause changing the storage size of its parameters, even if the function was targeted for the same machine. And the steps to build an LLVM JIT to retarget the function that was discussed earlier are to initialize the native target of LLVM, initialize the ASM printer for the native target, then choose the target corresponding to the underlying machine from the LLVM available targets, then get the LLVM IR of the application code in the module to compile the LLVM IR to machine code, and run the compiled function. The example below of how to build a JIT using LLVM can be found in reference 5. This is the example for the steps discussed earlier. So first thing, initialize the LLVM targets. Please notice that specific functions and classes of LLVM are used. Then the next step, initialize the ASM printer of the native target. Select the target that corresponds to the underlying machine and then generate code. That function is specific to each JIT compiler you build. For instance, if you need to build a JIT for executing a mapping algorithm, like in this work, then you would need to generate the LLVM IR for the mapping algorithm and insert it into the JIT module to be compiled. And in this case, code generation function generates the retargeted LLVM IR for the function into the compiled JIT module. And this code concerns compiling the LLVM IR to machine code. So first initialize the target specific layouts, get a pointer to the link layer, pass the link layer object to the compile layer object that is created here, add the JIT module into the compiled layer. And this is the code that concerns running the compiled code, the native code. So first, to do that, you need to get the symbol for the retargeted function, then get the function pointer to the retargeted function, then print the result of calling the function that was retargeted to run on another machine. So basically, that's what the JIT does. Prints the result of a function execution on another machine. Use case 2 of using a JIT compiler concerns actually the scope of this work, having the mapping algorithm executed before the application using a JIT compiler. So to do that, having the code that gives the hardware architecture details in the JIT compiler executed, followed by a mapping algorithm execution, can give a binary to execution, performing an architecture-based mapping for the underlying architecture. So the steps to build an LLVM JIT for this use case that concerns getting the hardware architecture details and execute the mapping algorithm before application runtime are to initialize the native targets, initialize the ASM printer for the native targets, choose the target corresponding to the underlying machine for the LLVM available targets. So far, so good. This is specific. This is common to method 1, use case 1. But now we will get into the specifics of use case 2. So get the LLVM IR representing the mapping algorithm in the module to compile. We do the same thing for the application code. We get the LLVM IR representing the application code in the module to compile. We then compile the LLVM IR representing the mapping algorithm to machine code. We do the same thing with the mapping algorithm. We compile the LLVM IR representing the application code to machine code. Then we get the number of logical cores and the number of logical cores per CPU using the comments in the beginning of the presentation. Then we run the compiled mapping algorithm in reference tree, passing the arguments, the hardware details above. So if we want to get into the last step, we need to follow the following slide, which discusses this step. So depending on the degree of communication with other threads and on the position in the generation hierarchy of threads, add each thread in a representation that can be either a graph or a tree that describes the communication between the threads. obtain the mapping result in either a graph-based or a tree-based representation, and with adding each thread in the chosen representation, set its CPU affinity, that is, set the course on which each thread would run. And then simply run the application code. That was all with method 2. Method 1 and method 2 would concern executing the mapping algorithm before runtime by adding the mapping algorithm in the IR of the application code. So the mapping algorithm and code getting the hardware details can be inserted in the intermediate representation input code, while compilation is going to be applied to the resulting and the mapping algorithm run before the application. Those are the steps to insert the mapping algorithm and the hardware details in the intermediate representation of the input code. So we first insert comments in the beginning of the presentation returning the hardware details as instructions in front of the application IR by using LLVM IR. Then we create an instruction for each in the mapping algorithm and make the compiler insert it in the application IR. Then we compile the resulting IR containing the code getting the hardware details, the mapping algorithm, and the application code. I have made a comparison between the two methods. So first method concerns using a JIT compiler to run the mapping algorithm before the application starts. And the second method is about attaching the intermediate representation of the mapping algorithm to the intermediate representation of the application in the beginning of the application, so that both will be executed at runtime. So the first remark for method 1 is that it is easier to implement, requires shallow knowledge about LLVM IR and constructing an LLVM JIT, and requires less time than method 2 that requires knowing LLVM IR implementation specifics for inserting instructions in the code. Then using a JIT in case of the first method seems to be less time consuming, as the mapping algorithm is executed once per underlying machine. A pointer is returned and can be stored so that the application is run for the second time on the same machine without executing the mapping algorithm. Then, on the other hand, for the second method, that requires more time since the native code corresponding to the mapping algorithm is part of the overall native code of the application. Improvements can be done by skipping the native code corresponding to the algorithm when the application is second time run on the same machine. Then the last remark for method 1 is that it can be easier adapted to another JIT builder than LLVM. In contrast to method 2, which uses code inserting the mapping algorithm in the application that is compiler dependent. In conclusion, getting the architecture details can be done by reading the CPU info file which is written at system startup. Efficient thread mapping algorithms require dynamic adaptation of the parameters describing the hardware, depending on the underlying architecture. Architecture-based thread mapping can be done at compile time, either by using a JIT compiler or by inserting the mapping algorithm IR at compile time in the beginning of the application IR, so that in both cases the mapping algorithm is run once, and that is for the first time the application is run on a machine. This is the bibliography of the presentation. Thank you for your attention, and moving on to the last part of this presentation, which is concerning the questions from you.
Iulia, lovely, perfect. Thank you so much for your great presentation. This is Code Dive. Stay tuned for more. Don't go away. We'll take a short break now. This is Code Dive, and our next speaker is Oleksii Pilkevych. Now, Oleksii is a student at Wrocław University of Science and Technology and works at Nokia as Python developer for test automation. He loves sports and psychology and stand-up comedy, and if triggered, he can go on about prog metal bands on N, and he can talk about it until your head explodes. So his talk is called Async. Oh wait, Oleksii, so some prog metal references are fine, but explosions, well, maybe not today. Other than that, off you go.
I always wished I could drink coffee like that from the comfort of my own home on other code dives. Now, today we are going to talk about Async I/O, and I am going to present how I would like to have Async I/O taught to me when I was first starting out. So, if you are already an experienced programmer and experienced with Async I/O, this might be a little bit boring for you, but you still might find something interesting in the way I give my own spin to the basics of Async I/O. If you are a beginner, it should give you a solid foundation. So let's get started. There comes a time when you want to do a bunch of stuff at the same time. And when such need arises, you remember that, oh, there's this framework in Python I heard about. It's called Async I/O. So you go to the internet and you copy the first Hello World example. It goes something like this. You write a normal function with a little bit of weird syntax, and then you run it. Also, in a bit of a weird way. And that works. It prints hello, sleeps for 1 second, and prints goodbye. But you might notice it's not happening at the same time. So if you're like me, you think, aha, I need to have 2 of those. So you make another function and you decide to call the first one twice from it. So far, so good. Let's run it. Turns out it's still happening sequentially. So why is that? Because intuitively, when you look at this await, it kind of tells Python, okay, at this point, you are free to do whatever you want to do, and you can then come back to finish it later, right? Well, turns out no, because it's not happening at the same time. So then you go to the docs and you find out that what you have to do is you have to use some kind of Async I/O function to wrap those 2 coroutines into one awaitable object. And once you do that, using Async I/O gather, you can notice, finally, that it's happening at the same time. Now, honestly, the first time I did something like this, I thought, okay, this works nicely. The only problem I have is that I'm using some weird functions here. So why don't I just go ahead and do the sleep the way sleeps in Python are done. And when you run it, you may notice it's happening sequentially again. So why is that? You're using this gather function to wrap those two coroutines. This coroutine has a sync keyword here. Oh, maybe you can await. Ouch. Turns out you can't. So this is the point where everything becomes just a little bit harder. So in this case, let's go to the basics. Recently I had a chance to teach Python to my girlfriend, and after an hour of me blabbering about how Python is great, unbelievable and amazing, we reached this example program. Yeah. And after we wrote it, I thought, okay, that's the point where you usually start learning about ifs, loops, and all other bells and whistles. But I thought, have we really explored everything in this example? And I started trying to complicate it with all the knowledge we had at this point. And I ended up with this little program. Yep. So what's interesting about it is it's very simple, but when I showed it to my friends, who are, not all of them are Python programmers, but very often they would get confused and they wouldn't give the right answer. So you can take a second to think about what this program is going to print to the screen. Nice, your second is over. So let's see what's happening. We nest a bunch of things together. We go to the most deeply nested one. And it's just a print function which isn't doing anything because it is not being executed. It's passed as an argument to another print function. Now, what does a print function do with its argument? It prints it to the screen. Now, we know how we print text to the screen, but how do we print a function to the screen? Well, in Python, a function is an object, and objects have magic methods which describe how those objects should be converted into text representation. So basically this should print whatever text representation is assigned to the print object. Now, after that, we print the result of the previous print function. Now, what is the result of a print function? Well, a print function shouldn't calculate any value for it, so it is not supposed to return anything. That's why we're getting none. So this should just print none. And that's what happens. Now, you may notice that for such a simple program, that's quite a complex explanation. But if you know how it works, most Python programs you read are going to be easy for you. Because no matter how clean code is or how much code there is, if you know that a function accepts arguments and returns value and are able to trace where that happens, you won't have any problem figuring out a complex code base. But still many people get confused with this program, right? So let's take this example to Async.io. But before we do, let's talk about generators, because generators are very interesting in the sense that very few people understand generators, and there's a good reason for it. Half of Python community is devoted to web development, which is the part I'm mostly busy doing most of the time. And usually, when you go to a Python interview and a question about generators arises, this is how it goes. The interviewer asks, "What are generators?" And you say, "Well, generators are those functions where you use yields instead of returns." And the interviewer goes, "Okay, so why would you need such a function?" And you say, "Well, if we wanted to generate a sequence of numbers, we wouldn't have to store all the numbers in the list, taking up a lot of memory. We could just generate them one at a time, and this way our program would be more memory efficient." At this point, interviewer says, "Okay, great job, let's move on to the next question." But the result is, that's a very primitive understanding of generators. And there is a point because we don't generate sequences of numbers in web development every day. But the problem is, if you want to do async I/O, you better understand the generator as well. So let's explore that a little bit. Let's say you have a sequence of numbers to generate. Let's say even numbers. So say you pass two values which define the bounds of your even numbers generated. And let's do it without generators. You create an empty list of numbers. If it's an even number, you append it to the list. Fair enough. Now let's see if our function works. And it does. Where the problem is that if you were to go a little bit beyond, you would have to wait until the numbers are printed out. But what if we do it using generators? So first of all, we remove this return statement, we remove this list, and we just add a yield here, right? You may notice that it doesn't work the way we're used to have it work. So what do? When we run this function, we get a generator object, which doesn't do much by itself. Similarly, if we execute an async function like that, we are going to get a coroutine, which is not going to run by itself. So what do? Well, let's assign this generator to a variable. So what can we do with a generator? Well, we can pass it to the next function. And this way, we are going to get the next consecutive value from this generator. So basically, we're moving on to the next yield using this loop. Now, you may notice that if we do this enough times, we are going to get an exception. So why is that? Well, if there are no more yields left to yield for a generator, it throws a stop iteration error. But fun thing is, if we loop over a generator, we don't see that exception. And if we do it like this, the numbers are being printed out from the beginning. So why is that? Well, that is because a for loop handles this exception for you. But for the sake of it, let's rewrite this program using a while loop. So let's say while true, we are going to take the next number and print it. Now, if we do it like that, we'll reach a stop iteration exception. So let's handle that. And there's a program. Now, what if we wanted to have two of those? And say we want to generate numbers from the number 100 to 110. Now, one thing we could do is we could do something like this. So you may notice that if we do it like this, those generators are being ran at the same time. Interesting, huh? Problem is this program hangs. It hangs because here I forgot to break the loop. But the problem is if we break the loop, this is a little bit dangerous, because if we have more generators, we might break before all generators complete. Maybe we break when the first raises stop iteration. So let's handle that quickly. Let's wrap it into a function, or let's call it loop. We're going to pass a bunch of generators in. Then here we are going to iterate over those generators, and we are going to try to get the next value. But we would also like to get rid of those generators that are completed. So we are going to delete those generators we do not need. Also, we have to check in this while loop if there are any generators remaining. And if not, we're going to end the loop. So let's see how that works. And that works perfectly. Our program executes and terminates. Now let's review how this works. So we create two generators, because it's important to understand it, because it gets confusing very quickly. So we create two of those generators, Those are generator objects which we pass in a list. We start an infinite loop. We check if this list is not empty. If it's not empty, we go and run this for loop. If it's empty, we exit. So if it's not empty, we iterate over those generators. So in this case, we go to even numbers generator, which counts from 0 to 10. We try to get the next value from it. If everything's fine, we print it, which you can see here. And then we go to the next generator in the loop, which is this one, which counts from 100 to 110. We print the value, and then we go back to the start of the while loop. We check if there are any generators left. There are. We go to the for loop. We repeat this until the first generator hits stop iteration error. We delete the generator, go to the next one, print the value, delete the generator, go to the start of the while loop. There are no more generators. We return. And that's how it works. Now, what if we try to apply it to the example in the beginning? So instead of generating even numbers, we're gonna say hello, get rid of the arguments, print hello, import time, sleep for 1 second, print goodbye. Get rid of this and create two generator objects. Remember, we have to call those, because if we don't, this is just a function, this is a generator object. Refer to the example with print in the beginning. Now, jokes aside, let's run it and see how it goes. And we have exactly the same situation we had in the beginning. Now, this is unexpected. Oh, correct. This is not a generator. So let's put a yield here. And let's get rid of this print statement, because our generator doesn't yield any value. It yields a none. So you can see that now it starts to happen at the same time, which is interesting. Now let's just quickly recap what this yield is doing here, because this is the point where it might get just a little bit too confusing. So we go into this loop with those two generators. And what happens is we start looping over them. We get the first one. We execute next on it. So this function is being executed. We print hello. We reach a yield, and this is when this next function returns. So at this point, we go to the next generator, which is this one. We print hello, and we yield, and the next function returns. For loop finishes, we go back to the start of the while loop, we start the for loop again, and we try to execute next on this generator. Now this yield is finished, so we go to the sleep function, we sleep for 2 seconds, we print goodbye, and we raise a stop iteration error. This generator is deleted, we go back to the for loop, same thing happens for the second generator, and we go back to the start of the while loop, no generators are left, we terminate. And this is exactly how it works. But if you look closely, you may notice that those two hellos are printed instantly. Then we sleep for 2 seconds before goodbye, and then we sleep again for 2 seconds. And that's not what we want, because we want to sleep simultaneously. We want those two goodbyes to be printed at the same time. So how do we do it? Well, you see, this program is synchronous. and it executes sequentially, deterministically. So if we have this time.sleep, here this program has to sleep for 2 seconds. We can't get around that. So maybe we can implement our fake sleep. What if this loop would get a lot of yields here, which would yield chaotically for 2 seconds before we can resume again? Now that might be a fair solution. Let's say we have start time here, and then we create a loop which loops until 2 seconds pass. So we say if current time minus start is less than 2 seconds, then we are going to yield. And we may remove this one. So let's see what happens. 2 hellos are printed, 2 goodbyes are printed. Ladies and gentlemen, we just invented Async IO. Now let's just think about it. So we run the first generator, print hello, go here, start this loop, we yield, so we move on to the next generator. When the next generator does the same thing, we come back to the first one, we go to the next iteration of the loop. Now it happens very quickly. And this is false, because 2 seconds haven't passed yet. So we yield again. And then this happens until 2 seconds pass and first generator completes, then instantly we go to the next one. Now, this code can start getting a little bit messy, so let's make a sleep function for it. We say for how many seconds we want to sleep. We copy this code here. So what do? We say sleep for 2 seconds. We write a yield here. Because if we don't, this is not going to be a generator. We're going to get an error here. Actually, let's do just that. We get an error, non-type object is not an iterator, which is quite confusing. But this happens because we pass a normal function to next. Actually, no, we're not passing a normal function, because here we execute hello. Instead of yielding, we return none, because that's the default return in Python. So here we are passing 2 non-values, we try to run next on a non, and we get this beautiful little error. So let's not do that. Let's add a yield here and run the program. Now, it may seem like the program works, but you may notice we're not sleeping. That's not what we want. Now, that is happening because here we create a generator object and we yield it, so this is completed instantly. Basically, this function is not fired. Now, how do we do that? Because that's a valid behavior, right? So in Python, there is this yield from syntax. And basically, this means that we want to run next here, and we want to basically redirect whatever this function yields. And again, our program works. So what we do here is we invented Async IO. So let's maybe try it out with Async IO. Let's say we create a main function, which is a coroutine. And in this function, we replace our loop with async.io gather. And instead of having this stuff in a list, we're going to do it this way, because that's the way Async.io API is designed. We run our main function, we get rid of this loop, and if we run it, it works exactly the same way. So notice that here we are not passing coroutines. We are passing generators, which I don't think this is even supported by Async.io API. But since there's duck typing, which means if we can yield from it, then it's a coroutine. It works. Now, this is all beautiful, right? But there's one strange thing. We still have this very weird sleep here. So you may say, okay, we have a simple example to demonstrate how Async.io works. But what if we want to use some libraries we love? What if we want to use requests? What if we want to use database clients? Are we going to have to write our own database clients which specify at which points we may go ahead and run something else while we wait? And the answer is yes. And that's a big problem, right? If you want to do Async.io, you have to have libraries that support Async.io and explicitly say where we want to stop doing whatever we're doing and move on to another thing while we are waiting for results. So what if we do not want to do that? Well, there is a way. What if there was absolutely no way to implement sleeping in our own way? So we would go here and we would sleep for 2 seconds. We would get rid of this and we would get rid of Async.io. We would make a thread out of hello. Then we would make another thread. Then we would start those threads. Now you may notice that we get almost the same result. What's beautiful here is that we don't have to implement our own sleep function. So what's all this hype with Async.io? Why can't we just use threads? Now, the problem with threads is that threads have no idea when we actually want to wait for something. So what might happen, if we have a program that does a bunch of stuff here before sleep and a bunch of stuff here after sleep, we might switch to the next thread not while we are sleeping, but while we are doing something else. And the problem with threads in Python is that we have something called the GIL, which basically says, in Python, you cannot run multiple threads at the same time. So basically, Python has a bunch of those threads, and it switches at regular intervals between those threads. Now you may ask, why? What's the point of it? If we have 10 threads and we can only execute one at a time, why bother having 10 threads? Why can't we just write an asynchronous program without threads? It shouldn't be any faster, right? Well, not always, because look at this program. Even though only one thread is executed at a time, basically we switch between those all the time. But if we switch during the sleep function, basically we optimize it, right? Because we may switch between those two threads during those 2 seconds, but because we were switching, this sleep function got started in both threads at the same time. Maybe a better explanation would be a network request, right? If you send 5 network requests and wait for a response from each of them, that's long. But if you use threads and you switch between them and you run one thread at a time, you still are going to fire those 5 requests almost at the same time, right? They would be fired one after another, but you wouldn't wait for a response before you fire another request. And basically, threads in this example work like stupid coroutines which don't know what are the best places to switch execution to another coroutine, but they do it at specific intervals. So what should we use? Should we use threads? Should we use Async.io? Well, it depends. And to demonstrate it, let's switch to some more complicated examples. So check this out. Let's say we want to run 4,000 of those hellos. Each one sleeps for 3 seconds. Now here we have an example with Async.io. What we are doing is we are creating 4,000 coroutines. Each coroutine just sleeps for 3 seconds, and we measure the time it takes to finish this program in a quite naive way. But let's see what happens. 4,000 coroutines we finish in 3 seconds. That's impressive. Now let's do it using threads. Very similar. Create 4,000 threads, start measuring, run all those threads, wait for all of those threads to finish. Easy peasy. We run the program. Takes a bit longer. Why? Well, you have to create those threads. And to create threads, you have to copy a little bit of memory between them. And those switches between threads, they take time. Now, in this case, everything is happening cooperatively. And it makes sense. We bothered to write a whole new sleep function. We would like to have a better performance. Now, we also have another way to run a bunch of things at the same time. And this another way is using processes. Now, there is a big difference between processing and threads. You can't execute a bunch of threads at the same time, but you can execute a bunch of processes at the same time. Why is that? Because in case of processes, we are actually going to run 4,000 Pythons at the same time. When we use threads, we run one Python interpreter, which has a bunch of threads to deal with. Here, we run 4,000 Python processes, which are all synchronous, but since there's a bunch of them, they're happening at the same time. Now let's see how well this program performs. And you may notice that it doesn't perform that well. Now, why is that, you may ask? Well, that's because we are running 4,000 Pythons on one system. It's heavy for this little PC. So this looks like a disaster, right? Let's terminate it. question is, what's the point of having processes if they are so heavy and so slow? Well, let's look at a bunch of other examples. So instead of sleeping, we are going to send network requests. So let's go to Async.io. Here's what we are going to do. We are going to send 200 requests to Google. Sorry, Google, for doing this. In this example, I wanted to spin up my own server and do it on my own server. The problem with that is my server wouldn't handle 200 requests happening almost at the same time. So our measurements wouldn't be accurate. So basically we are DDoSing Google, but Google is smart. Google is going to notice we're doing that, and Google is going to just reject those requests quickly. But the speed of one such rejection is still an HTTP response. So it's still fine to test it, to test this program with such a network request. So let's see what happens. We create 200 coroutines. Each coroutine creates a session and sends a GET request to Google. Easy peasy. Let's see how it runs. Beautiful. We just sent 200 network requests in 1 second. Let's do it using threads. Again, same thing. 200 threads, 200 requests to Google. And you may notice that in case of Async.io, we're using a different library, which supports Async.io. Running the example with threads takes 5 seconds. Still a good result. Now let's run 200 processes. And we're starting to get disappointed because the results are very similar to... Actually, we perform a bit better here. But notice that here I've been measuring this time when we already created 200 processes. So you may see that this process of creating processes is very time consuming and their execution is fairly quick. But still, it performed the worst of all, and Async.io was the clear winner here. But let's switch our examples up a little bit. So we are going to go and run another example. Up. Okay, so what we are doing here is we are going to have a coroutine which sleeps for 1 second and then decides to check if this number is prime. Now, this number is not prime. That's why this silly algorithm is going to take a long time to figure that out. Roughly 1 second. And we run 5 of those coroutines. Let's see how it performs. And it takes 7 seconds. So why is that? Well, what happens is those sleeps are happening simultaneously. But then we have a task. Sorry, not a task, we have a function. We have a function which is blocking. We are running some numbers through it. And on our computer, our CPU does that. So since only one thread is being executed, it happens sequentially. We can't just tell our CPU to somehow clone itself and count those prime numbers at the same time. So that's why Async IO has no possible way of optimizing this function. Now let's run it using threads. And you may notice that we have similar results. In fact, almost identical. So in this case, threads perform just as well as Async IO. Now, if we have a bunch of threads, why doesn't this happen quicker? Well, same thing. Here you can notice how this GIL actually works, because if we could execute those threads at the same time, then we could run those calculations in parallel, right? But we can't, because only one thread is happening at the same time. So actually here we are switching between different threads as they're doing this calculation, and that's just slowing us down. There's no point in that. So that's why we get a similar result. But let's do it with multiprocessing and run 5 processes. Now that happened in 3 seconds, and here we actually measured everything from creating those processes to executing them. So it happened much faster. It happened 2 times faster than everything else. And why is that? Well, here we have the sleep, which Async IO and threads deal with really nicely. Multiprocessing deals with it just as well, because even though we have 5 threads which all run this function, all of those 5 threads hit this sleep, and those 5 processes hit this sleep, and they wait together at the same time, and then they execute this function. Each process executes its own version of this function at the same time. So that's why we're getting such enormous speeds here. So what's better? Threads, multiprocessing, or Async IO? I guess by this point you know that it depends, right? But let me show you one more example. So what we would like to do in this case, let's go to Async IO. We are going to send 10 requests to Google. But before we do that, we run the prime number function. We send those 10 requests, we run this prime function again. And we use Async IO for that. Now here's what's happening. We run those functions sequentially to check if this number is prime. We run those requests almost at the same time, and then we run this function again sequentially. And it takes us 13 seconds. Let's do the same thing with threads. Now at this point, you may predict what the result is going to be, right? And results are roughly the same as they are for Async IO. A little bit longer than 13 seconds, which is expected, right? Now let's do it with processes. Now we may expect that processes are going to make this faster, right? We finish in 5 seconds. But here's the thing. What if we have to do it 500 times, right? We know our machine is not going to cope with that as well. And here, but let's think of it, right? What are the strengths of Async.io? Async.io is really great if you have to wait for an input-output operation. Now, when is Async.io not that great? When you have to execute a CPU-bound task. But that's something multiprocessing is really good at. So, here's one thing we could do. Why don't we just combine both of them? So here what we are going to do is we are going to execute 5 processes, but each process is going to have its own event loop, and each process is going to run this coroutine where it looks for a prime number, sends 10 requests, and then looks for a prime number again. Now you may notice that in case of the multiprocessing example before, what we did was we would run 5 processes here, but each process would have to send 10 requests sequentially. But what if each process had its own Async.io and could send those 10 requests at the same time and then wait for results? Well, that's what we did here. And it gave us the best speed of all. Now, to be honest, this is not my idea. This idea is from talk by John Rees on Async.io and multiprocessing. And he combines this stuff into, I believe, AIO multiprocessing library. I tried to use that library for this example, but somehow I didn't manage to get the speeds I got by just doing this manually without a library. I'm not sure if I wasn't doing something correct, but that's the thing here. I will show you one more example. Let's say we have a cat. Cats are great, right? So why don't we have one? Now, this cat can do a whole bunch of things. It can eat. It can have free time. And by free time, I mean sleep. Why do we have this function in the middle here? Why can't we just sleep if that's the only thing he does? Well, you will notice in a minute. So we have 5 synchronous cats, and we let each cat exist for a little bit. So what happens is one cat starts eating, gets some free time, sleeps, wakes up, eats. So it's slow. Basically, those cats take turns existing. Not nice, right? So let's say we wanted to optimize it. Well, we may create an async cat, right? We could say, okay, import async.io, and please create those cats, and cat exists for cat in cats. Unpack this, and there we go, right? We could make this a coroutine. And now we have everything. Oh, right. We have to use gather for it. and we run it, it's still synchronous, but let's say that this sync cat comes from a library, which we can't edit. So our solution would be either to copy the library, make this stuff async, right? Or we could just create an async cat, which inherits the synchronous cat and switches things up a bit. But let's say that this have free time. Switches things up a bit, right? So here we would await, have some free time. In have some free time, we would await sleep. We would make this a coroutine. We would copy the sleep function. And then we would await async sleep. And then use this async cat instead of the sync cat. And we wouldn't touch the eat method because there's no way we could optimize it, right? So let's run it. And you may see that it's quite fast. All the cats go to sleep at the same time, all the cats wake up at the same time. But what if this have some free time function has a lot more code, right? And what if for some reason we can't modify it? For example, maybe this function uses some stuff from C, and the library is being compiled to C, so when you import it into Python, you don't have access to the source code of this function, you just know that it calls sleep. So can you make it call sleep, but for sleep to somehow underneath switch itself to a coroutine? That's the first idea I got, because I like to do weird stuff. But as much as I tried, I couldn't succeed at it. So what you could do is you would have to turn to our dear friend threads, which weren't performing the best, but remember those had an advantage because you didn't have to rewrite everything to async to use the benefits of threads when it comes to IO-bound tasks. So let's see how it plays out. In the exist method, we get the event loop and we use something called run-in executor, and we pass the synchronous function to this executor. This none means that we are going to use the default executor, which is thread pool executor. In Async you also have the multiprocess executor, but in this case we want to optimize something that is not CPU bound, so thread executor would be a better option for us, right? And basically that's what we do. We do not touch any of those functions. We make this into a coroutine, and actually this is unnecessary. We make this into a coroutine. Let's say we inherit here, right? And let's see how it performs. It performs very similarly to the first Async example. So we basically managed to get around this problem without having to rewrite everything to Async using threads in the spot where we can't use Async and using Async for the rest. And that's pretty cool. And what's cool about it is that we can take advantage of both Async I/O, threading, and multiprocesses to solve different kinds of problems. And we don't have to use something exclusively, and we don't have to fight over what's better, because everything is better for different kinds of problems. Now, question is, where can you go from here? First of all, check out John Reese's talks on Async I/O. Those are phenomenal. This is the Thinking Outside the Jill talk, where he discusses how we could take advantage of Async I/O and multiprocessing. Also, from John Rees, we have a talk which is called What is a Coroutine Anyway? And in this talk, he explores how coroutines work underneath in depth. And it's also very, very, very informative. Next thing is check out Thinking About Concurrency. And this is a talk by Raymond Hettinger. There are two versions of it. Both are amazing. Basically, he explains the idea I explained, or better say, I just explained what he explained. Now, one other thing with Async I/O is its API is changing rapidly. So watching talks made by core developers of Async I/O, where they discuss changes to the API and what they plan to change, or what they think was a bad design in the past but maybe a better design in the future, is also very, very helpful. I can also recommend this talk by Andrew Svetlov. He's also a core developer, and he explores some of the things you shouldn't do in Async I/O. And this information is also a goldmine, because some of the points he makes I couldn't find anywhere else. And one another talk recommend with all of my heart is Łukasz Langa's Async I/O and Music, which he did on the previous code dive, and that talk is phenomenal because he shows you a completely different take on Async I/O and shows you what you can do with Async I/O apart from sending network requests at the same time. So he just controls MIDI synthesizers from his code simultaneously using Async I/O. So that's amazing. Now, thanks a lot for sticking with me for this talk. Let me know what you liked, what you didn't like, and what I could do better. Definitely, if you're interested in the topic, check out the talks I showed in the end. And have fun at Code Dive. See you very soon, probably in a year. Not sure about that, but you can still find me by the links in the description, chat, and see you soon. Thanks for your attention, and thanks for sticking around.
Oleksii, thank you very much. Great presentation. This is Code Dive. Don't go away. We're going to take a short break, but stay tuned for more. Hello, welcome back. Our next speaker is Daniel Aronsson. Now, Daniel is a senior application engineer at MathWorks. He specializes in signal processing and communications system design. He has several years of experience in these fields, and he also works regularly with computer vision and FPGA system implementation. He holds a PhD degree in wireless communications from Uppsala University and in Sweden, specifically on MIMO channel prediction. So, raising the abstraction level, let's put our virtual hands together for Daniel Aronsson.
So thank you for that introduction, and welcome to this presentation on raising the abstraction level. Here we will talk about how you can use a dynamically typed high-level language, MATLAB, as a kind of an extra compiler on top of your C compiler to raise the abstraction level, to quickly get from a few simple lines in MATLAB all the way to readable C or C++ or CUDA code. All this will be done completely automatically by using tools that we will look at today. But before we get there, let's spend a few minutes on what MATLAB is for those of you who are not too familiar with it. So what is MATLAB? So as most of you are familiar with, I think MATLAB is a complete programming language together with an IDE. It's a powerful software environment that is really built for engineers to quickly get started and get doing what they need to do. It's easy to learn and to code and scale up to bigger projects, and it's built in a rigorous way so that everything is thoroughly tested and fully documented. You add functionality to MATLAB by adding toolboxes. So if you work on a specific field, you can simply add the toolbox that is associated with that field, and that will allow you to build up the total functionality at hand. What we try to do when we build MATLAB and build these toolboxes is to have interactive apps to go with the toolboxes that will allow you to quickly get started and doing things by point and click. And once you have everything set up the way you want it, you can then automatically generate MATLAB code out of that. To do what you've just done by point and click, you can then do programmatically. So that will allow you to quickly get started with your programming projects. But then what we're going to talk about today is that once you have that MATLAB code written, how do you get from there to C or C++ code? And there we have something called MATLAB Coder that will allow you to take a MATLAB function and really translate that into C code. And if you think about it, it's quite a difference between MATLAB code and C code, because MATLAB is a dynamically typed language, right? So everything is all the data types, all the variables have data types and sizes that are really decided runtime. So you can change the data type and you can change the size as you go. In C that is not so. So in C everything needs to be statically typed. So going from MATLAB to C is quite an undertaking, and that is where MATLAB Coder will help you. So there are a few different use cases. So in going from MATLAB to C, some people want to just generate C code to hand that off to software engineers. Other people want to sit on the same, sit on both chairs, so to speak, so that they both are coding in MATLAB and C, and they want to integrate their generated code directly into their bigger C projects. Some people also want to prototype their MATLAB algorithms as standalone executables, and that is also something that you can do with this tool. And lastly, some people want to stay in MATLAB, but they want to use automatic C code generation to speed up their algorithms. What we're going to focus on today is really the first one, or the first two ones, where you quickly go from MATLAB to something that is readable in C, and you can hand that off to software engineers. So that is what we're going to talk about today. You may ask yourself, what is it that you, what kind of algorithms is it that you can actually translate to C code? And a few years back, the support was actually quite limited. But as the years went by and we expanded of the capabilities of MATLAB Coder, we now see that actually most things that you can do in MATLAB will actually translate automatically to C via MATLAB Coder. So there are a few functionalities that are still not supported, but they are getting very scarce. As I mentioned before, you add upon the functionality that you have at hand by adding toolboxes to MATLAB. And the same goes for automatic C code generation. So most toolboxes that we have functionalities that support automatic C code generation. So let's say you work on I don't know, automated driving, and you write your algorithm for tracking the cars around you. Then you can quickly prototype that in MATLAB and automatically generate C out of that. If on the other hand you work on, I don't know, 5G, then you add 5G toolbox, and by so you get functionality for let's say a polar decoder that you're working on. You can then take the polar decoder that comes with 5G toolbox and automatically generate C out of that. So by adding toolboxes, you actually have a lot of functionality at your fingertips. So most people that I talk to when it comes to automatic C code generation are people that are experts on digital signal processing. But they may not be as versed with writing C code. So what they want to do is to take their DSP expertise and add MATLAB Coder to sort of automatically bring in that knowledge of C to produce a DSP algorithm written in C. Now I expect that many of you on the call today are actually C programmers. On the other hand, you may not have all the expertise in DSP that some projects may ask for. So you can actually do the opposite thing here, to use your C expertise and use MATLAB Coder to bring in that DSP expertise. So as we just saw on the slide before, let's say you have a filter, a signal filter, or a signal decimator or something like that, or an FFT. And you need to produce an algorithm written in C that uses that kind of maths. Then you can use MATLAB plus the right toolbox to actually automatically generate a function for that digital signal processing and bring that into your handwritten C project. So it's really a way also to use MATLAB's functionality for all the digital signal processing that are in there, and use MATLAB Coder to bring in that as automatically generated C code. So today I'm going to use a very simple example here to show the capabilities of automatic C code generation. I'm going to use a filter as an example. So what does a filter do? Well, you have some input coming into a filter that illustrated by x0, x1, x2 and so on, and out comes y0, y1 and y2 and so on. And inside that filter you have a few coefficients. In this case I've chosen to have 5 coefficients, and really what comes out on the filter, on the output of the filter, is a weighted sum of the inputs, right? So the fifth output of the filter will be a weighted sum of the first 5 inputs to the filter, as you see here. And the next sample that comes out will be a weighted sum of the inputs number 2 through number 6, and so on and so forth. So that's how a digital filter works. And you can more compactly write that on vector form. So you say vector y equals some matrix A times these filter coefficients, where A is then comprised of the inputs, as you see here. So I'm basically building up the inputs coming in for the different 5 time shifts here. And so in this case we're going to ask ourselves what are the coefficients of this filter. So we imagine a filter but the coefficients are unknown. Application here could be in wireless communications. So you have a wireless communications channel, a fading channel, and you don't know the coefficients of that channel. Or it could be an maybe power amplifier, and you need to model that power amplifier, and you need to figure out how to model that. May not be a linear model in that case, but I mean, more or less, you'd have this kind of problem there. So finding unknown filter coefficients is a fairly general problem, you could say. So this is what we want to do here. So how do we go about doing that? So we take that vector formulation that we see there, we write it even more compactly, so we say vector y equals matrix A times a vector h. We want to find that vector h, and in MATLAB that's trivial because you use the backslash operator. So we say h hat. By hat here I mean that it's an estimate of h. So h hat equals a backslash y, and that's it. That's all you have to do to find an estimate of these unknown filter coefficients h. So that's what we're going to look at here. So with that, let me go to MATLAB. So I'm going to bring in my MATLAB window here, so that you can see that, hopefully. So what we're going to do here is to start and say edit function m. I'm going to write my my function there to find these filter coefficients. So I'm going to say h hat equals some function. I'm going to just call it fcn here. It's a bad coding practice, I know. And we're going to take the input to the filter and the output coming out of the filter, and from there we're going to find the unknown coefficients that we just saw. And as you saw, the simple way of doing that is just to take some matrix A backslash y, and then of course we need to form that matrix A. So I'm going to say here x, the input x from the fifth element all the way to the end, and then the fourth element all the way to end except 1, the third element all the way to end except 2. Notice here that I'm actually hard coding the length of the filter. I mean, more ideally I might want to do something that could take any length of filter, but here I'm going to keep it simple and hard code the length of the filter 5. So that's my function, and then to go with that I will probably want to write some test script. So I'm going to create a test script there that I'm calling the function name _tb for test bench. So that's something that's fairly common. And in this case I'm going to test it. So I'm going to say, okay, we use some random input to the filter. So 10,000 random values. And here I'm going to make up some filter coefficients, and these are really the coefficients that I want to recover. And I'm going to say just 5 values here. Could be anything, but I'm just going to pick 0, 1, 0.8, 0.6, and so on and so forth and so on. So that's my filter coefficients. What comes out? Well, that's just, so y, that's the output of the filter, and that is going to be the filter coefficients. 1 for the denominator, this is an FIR filter, and this is what comes out. Okay, so that's the reality, and from the reality I'm going to then test my function on the inputs and outputs there, and to see if I can recover that h I had there. So in this case I'm going to do this. They will probably come out in different orders, but that doesn't really matter. So if I run this now, I did some error here. So let's see, what did I do? 5 and 4 and 3 and 2 and, okay, I made a typo there in the, and it should be and -1, -2, -3 and -4. This is what happens when you do things live. And then I made some other error. Let's see, what was that? Well, actually y should be probably the 5th up to the end, because I have a tail there that won't fit, so I need to cut away the 4 first elements here. So let's see if that is right. And now we call that, and actually let me go back and remove the semicolons. That means that if I remove the semicolons, I'm going to suppress the, if I have semicolons, I'm going to suppress the output. So now I get the output. And here you see that my correct input is there. That's these values, and what I get out are these values. They come out in different orders because the way I set it up, but that doesn't really matter. So you see the algorithm is now working here. So from there, the question is now, so now I have an algorithm that I have tested in MATLAB, and it's written in MATLAB and tested in MATLAB. And how would I go about to actually generate code for this? And what we're going to do now is to open up an app that is called, so if I go to the apps tab in MATLAB here, I will find an app that is called, so down here I have code generation, and it's called MATLAB Coder. So I'm going to open up that app. So as I mentioned in the beginning, we try to do it so that for the different toolboxes that we have, we try to have apps that will allow you to quickly get started with these tools. So the first thing it's going to ask me for is the function name. So I'm going to then point to that function, and then I'm going to go to next, and then the only thing actually that MATLAB Coder needs to understand when you generate code from MATLAB to C is what are the input data types and the input sizes, because from there it's going to be able to figure out all the sizes and types of all the internals in the function. And that is essential because in C you need to define those data types and sizes once and for all when you set up the function. So that is something that cannot be decided runtime as it's done in MATLAB, but it needs to be figured out from the beginning. But the only thing you need to provide is actually the types and sizes of the inputs, not all the internals like the matrix A in this case, because MATLAB Coder will be able to figure that out itself. So in this case, I could actually use the test script to get MATLAB Coder to figure out these types and sizes from the test script directly. Here I'm going to actually do it manually. So I'm going to say that I put in doubles here, and I'm putting in a vector, a 10,000 by 1 vector of type double. The same for y, so I'm going to 10,000. I hope this is not too small so that you can see it. So these are the input data types. Now I can click next. I will skip that one actually and go directly to code generation. So here I can actually choose what kind of output I want. So if you remember in the beginning, some people want to use this for speed up, and they can produce what's called a MEX function. Some people want to produce a static library or dynamic library. You can do it here as well. In this case, I'm going to generate standalone readable just C code. So let's click on generate. I'm going to make this a little bit bigger. It takes a while for MATLAB Coder to go through all the transformations that are required going from MATLAB to C. So it takes a while to build that that C code, but it's worth the while. So what you will see here is that over here I have this source code. Actually, let me open up the report instead. So what you will see here is that this is the original function that I had. I can actually hover over the function and you can see the data types that MATLAB Coder has deduced. So you can see that this is actually a size 9996 by 5 matrix of type double. So you can hover over here and see that it makes sure that it got everything correctly. But everything is of course automatically done here. You can also trace the code, so I can click on trace MATLAB code, and here you will see the MATLAB code, and you will see the generate C code here. So if I click on a line here, I can actually take that line first, that puts together. You will see how that is reflected here, so you can see in the generated code how it loops over and sets together this matrix A, fills in all the values for the matrix A, and down here you will be able to see how the backslash operator, just a one-liner in MATLAB, is actually reflected in several, actually hundreds of lines in this case. But what you will see, so we can use that traceability to better understand what happens here, but what you will see, so let me turn that off and just go to the C code, is that these two lines in MATLAB has been generated, in this case, about 340 lines of C code. That is to be expected. To do this least squared solution the way the backslash operator is doing it is actually quite complicated. You need to do a lots of exceptions and things like that, and that needs to go into the code here. So you see how that our two lines was expanded into 340 lines. But something that is also evident here is that this may or may not be what you're looking for. So in this case, everything is implemented in a way you can say rather naively, and just in for loops. So it's by default generating ANSI C code that will compile on any platform. And we'll look at later how you can change the configuration and get something that is maybe a little bit more efficient, depending on what platform you have. But for now, just notice how easy it was to get from MATLAB to a few lines in MATLAB to many lines in C. So I'm going to close down that report. Something that you can do now, if I mentioned in the beginning, we have these apps that allow you to quickly get started, as we've seen here. Something else that something that we try to do with these apps is to, once you've done what you're looking for, you can actually generate MATLAB code out of that to automate it in the future. So in this case, I'm going to go to the menu here and say convert to script, and that will create a script that does this automatically does this directly from the command line, and we'll look at that. So I now automatically generated that script. So if we look at the script, you will see that I got a few lines, a few commands here that will do this from the command line. We'll look at that in a few short minutes. But before we leave the app, I'm going to show you one more thing. And that is, I'm going to go back all the way from the beginning, because something that we didn't look at here is that in the generated code, everything is statically typed here. So you see that all the data types here are actually, if I go down to my function prototype here, so it's further down somewhere here, you see that all the data types here are 10,000 long. So these are my input vectors, 10,000 long. And you will also see in the generated code, all my internals here are actually static sizes. This is likely what you want, because that means that you don't need to do any memory allocation via the operating system. Everything is statically typed, and you can compile this onto an embedded system, even without that doesn't even run an operating system. But so in many cases, this is exactly what you want. You want to be able to have a function in MATLAB that is very generic, and you can call it with any types. And then once you generate code from there, then you, in the code generation process, you do what we just did now. You say, generate code for this for specific sizes and get specialized code out of that. But in some cases, you may also want to produce more generic code. So I'm going to go back to the beginning, where we specify the sizes here. And I'm going to do something else. So you see I specify the size 10,000. I'm going to specify the sizes as colon 10,000, which means to up to 10,000. So that will allow my code to accept data sizes that are up to a certain size, but they can be smaller. I'm going to specify that and go back and see what happens then. So we go back, we are now reconfigured the code generation process to accept those dynamic data sizes, and I'm rebuilding the code. And what we'll see now, if I go down a little bit here, is that the function prototype that before took the static 10,000 x and y, now they have these other types that we define actually in files down here. So you see this called EMX API. So we define automatically, we generate out an API that will accept dynamic data sizes. So this will allow you to, I won't go down into any detail here, but this will allow you to, when you call this function, to specify data sizes that are dynamic. What is the drawback here? Well, if we go down in the code, you will see that it now uses function calls that look like this. So you have something called EMX, ensure capacity. So that means that every now and then in the code, the operating system needs to make sure that the generated code needs to make sure that the right amount of memory is allocated. So it needs to call out to these kind of functions. And if I were to go into that function, maybe I can go to the report here instead. So if I were to go into that, click into that function, you will see, so now it jumped to this emxutil.c that we generate together with the main function. You will see that it down here, it's going to use things like dynamic memory allocation, like calloc, so to call out to the operating system to allocate memory. And this may or may not be what you want. So if you need that kind of versatility in your generated code, then you can easily do that by just reconfigure the code like this. But you need to be aware of that you also get code that is more inefficient than if you would use static allocation. But with MATLAB Coder, it's just a matter of a small reconfiguration, as we just saw now. You don't need to change anything in the original MATLAB code. Okay, so with that, let me leave this app and go back to MATLAB, and go back to this script that we just saw. So what I'm going to do now is to note that what the way you call this from the command line is actually via, I'm going to clean up a little bit here. It's actually via, let's see, I think I took something away there. No, sorry, it's down here actually. So you call a function called cogen. That's how you generate code from the command line. So what we're going to do here is to, I'm going to tidy up a little bit, so remove that. So what we're going to do here is to call cogen, and I'm going to say this function is the function that we want to generate code for, and then I need to specify the arguments. In this case, I can just say the arguments is of the type X and Y that we already have in the workspace here. And then I'm going to use a configuration object, and that is simply saying encoder config lib. And this is essentially going to create for me a configuration object that generates standalone C code. So that's how easy it is to generate code from the command line. So I'm going to add a few extra ones. I'm going to say don't compile, only generate the code, and also launch the report once you're done. So I'm going to save that and run that. And this is going to do what we just saw. It's going to generate code for this, for statically typed static data sizes, and I'm going to get the report out. Okay, so that is That's how easy it is to do from the command line. So now we saw how I could go back and reconfigure, change the configuration to get dynamic memory allocation and so on. What I want to do here is to reconfigure the code in a different way. So when we do it like this, we will get a standard NCC code out that will compile on anything. But what we could also do is to use this configuration object. So if I were to, I'm going to clear everything in the command window, and I'm going to maximize it so we only see that, and look at this configuration object. You see that there are a lot of different settings that you can change here. So you can go in here and change everything that we can change in the app. You can change programmatically here. But one of the things that we can do here is to go in and say change something called a code replacement library. And I'm going to change that to I think it's called that. Yeah. Okay. So in this here I'm going to say actually generate C code, but generate it for a specific platform like this. So if I rerun this now, so I'm going to run this section that only runs lines 5 through 8. Takes a while, so you see down here it says busy, so it's now generating code. But now if we go into the generated code again, we shift down a little bit here, we're going to see that I get function calls that look a little bit strange like this. It's called mm256 store upd and so on and so forth. It's underscore mm256, and these are vector instructions that are specific to this Intel platform. So what happened here is that by just changing one configuration in this configuration object, I actually got what's called SIMD instructions, so vector instructions that are specific for this platform. So just by changing this, I got code that is essentially different from the ANSI code that I got up here, but will be much more efficient in that it's using vector instructions that only works for this processor when it carries out this this code, this least squares solution. There's one more thing before we move on that I would like to show you. It's quite a big thing, and I wish we had more time to go into detail here, but I'm going to remove this, and then I'm going to change this configuration to instead say coder.gpu config. I think the C should be capital here, and I'm going to call that instead. And this is actually going to call out to a tool that is not called MATLAB Coder but GPU Coder. And GPU Coder generates CUDA code that will run on NVIDIA GPUs. So what happens here is that the generated code now is actually called FCN, not .c but CU, which stands for CUDA. It looks like a little bit. It looks like C for the most part, but it's actually going to use. So if we look here, here's the function. So you see it looks like the function prototype looks the same as before with the static sizes, the 10,000 and 10,000 vectors coming in. But what's going to happen here is that it's going to allocate memory on the GPU, and then it's going to copy over the data from the CPU to the GPU and call out to these different kernels, and the kernels will execute massively parallel on the GPU. And once that is done, it's going to copy everything back to the CPU, and you get the results. So what happens here is that it generates this CUDA code, it generates these GPU kernels that you see here. That will be, you can go into the code here and see what they look like, and they will execute massively parallel on the different threads on the GPU. And everything is again, notice how little I changed. Actually, I just changed that line to get now the same code that small code again, but now get that in the form of GPU code. And if you remember the ANSI code that we had in the beginning, that was 340 lines, and now we're up to 760 lines just for the CUDA code, just to do this on the GPU. So it's a very small changes will allow you to do vastly different things and quickly test a lot of different solutions. And programming in GPU is not an easy undertaking, and it's really a problem of minimizing the transfer back and forth between the CPU and the GPU, and that is what one of the things that GPU coder is trying to minimize there. A lot of different more things that we could talk about here. Deep learning is a big topic that is very commonly common target for GPU coder and GPUs. So you can train a deep neural network, use that in MATLAB, and then generate CUDA code that will execute on the GPU for that. So the big topic that I now just spent 5 minutes on. But what I want to focus on here is how little I did to get 3 different versions of the same functionality in vastly different forms. So that was the short demo in MATLAB. Now I'm going to go back to my slides. So what we saw here is that with one design, while with 2 lines in MATLAB, we get multiple configurations. So ANSI code that will compile on anything by default, and then you can change this code replacement library setting and get platform specific code. In this case we got this vector SIMD instructions, and also if you have a GPU coder you can get CUDA code out. I mean, depending on the problem, it may not be that not all problems are a good fit for GPUs, but if they contain a lot of parallelism and linear algebra, or deep learning, then it's a good fit for GPUs, and then GPU coder is an interesting tool to take a look at. That's basically it, what I wanted to show you today. But before we finish, let me just bring a few extra topics into the picture here that we haven't dealt with. So one is that you may want to bring your own handwritten C code into the picture. So here I have a handwritten piece of code written in C on the left side, and on the right side you can see how you can integrate that into your MATLAB code. So you use this command called coder.ceval, and you point to the name of that function. And in this case, what you need to watch out for is that in this case we had a pointer. The first argument is a pointer, and then you use this coder.ref. The other one is just a regular value, and then you just insert that like that. But if it's a pointer, you use this coder.ref. Pointers don't exist otherwise in MATLAB. So, and if you were to generate C code out of this, you would see that it would just, this line, call out to your handwritten C code. So it's very easy to incorporate your own handwritten C code into your automatically generated C code. And the last thing I would like to mention is that once you have your generated C code, and it may then contain snippets of handwritten C code as well, you may want to check your code for runtime errors to mathematically prove that it's sound code. And we have a tool called Polyspace that will allow you to do that. So here I have a small piece of C code, and it may not be obvious whether this code is safe or not. And what Polyspace will allow you to do is to prove different things. So for example, it could say that it uses different colors. So for example, it could say that at that line it green lights that. So writing to that pointer like you do there, that's actually safe. It's sound. And you can see in the code that it may not be obvious if you're not very good at C that this is sound, but you can actually, the tool will prove that this is something that you can do. But then there's a problem here, because it can mathematically prove that this will be out of bounds. So that is a big red no-no there. It can also prove dead code. So in this case, we'll see that this code will never be reached, and it will mark that as gray. So that is dead code that you may not want there. Can also be things that are unproven. So in this case, we don't know what the value of I there, so the tool cannot prove whether this is green or red. And the last thing that it can do is that even if a line is programmatically sound, it may violate some coding standards. So in this case, it may violate the MISRA C coding standard. So it will warn for that as well if you need to comply with a certain coding habit there. So that is polyspace. And to finish off, I just want to summarize what we've done today. So first of all, we looked at MATLAB Coder and GPU Coder and how you can produce readable C, C++, and CUDA code from MATLAB. We used apps to quickly get started, so that's usually the first starting point. Start the app, play around with it, try to do whatever it is that you want to do, and then automatically generate MATLAB code out of that from that app to automate the process in the future. And then we looked at the different configurations that allow you to switch between dynamic and static memory allocation there. And also incorporation of handwritten C code by using the coder.ceval command. And lastly, polyspace is a tool that uses formal methods to prove the absence of critical runtime errors. So you can use that. Whether that is not in any way tied to MATLAB Coder and GPU Coder, it's something that you can use of any C code, even if everything is handwritten. Maybe especially if it's handwritten, actually. So that is what I wanted to show you today. So with that, thank you for attending. I hope you found it useful, and have a nice day.
Daniel, thank you so much for your presentation. That was perfect. We're going to take a short break now, but don't go away. Stay with us for more presentations at Code Dive. Hello and welcome back. This is Code Dive, and now we have a duo of speakers, Piotr, Pietroń and Filip Olszewski. Now, Piotr is a technical and agile coach with over 12 years of professional experience as a programmer, Scrum Master and software architect. He's lucky enough to have seen Agile function in all its glory, and ever since he's been eager to experiment with new ideas that could improve software development work. Privately, he likes to waste time on lost causes, such as trying to solve the unsolved Eternity 2 puzzle or trying to learn to play the guitar. Filip is a Java software engineer and Scrum Master here at Nokia. He's excited about software development and architecture, agile methodologies and, wait for it, Neapolitan pizza. He explores new solutions for accessible IT education and mentoring, and recently he started blogging at his own blog, filipolshev.blog. Gentlemen, over to you.
Thank you. So, hello everyone. Today we have a pleasure to share with you our experience from implementation of feature toggling platform. And the first question that we want to ask is, why feature toggling? What is so important or interesting in this concept? So first, we need to understand the current situation. Yes, everyone is evolving towards the continuous delivery, which means that we need to deliver more software in small batches and very often. And why is it so that we are not doing this already? Well, let's look at our continuous delivery pipeline. So it consists, when we finish a feature, then we push it to the pipeline, and if we are lucky, it will end up in the production for the customer. But not always it happens like that. Sometimes we fail the production and we blow up the product. Especially when we work in a bigger team, the chance that we will break something will be much bigger. So what can we do then if this happens? Well, at this point we need to, for example, roll back all the features that we have provided and try to repair the situation. So to make it somehow less risky, we can introduce the verification environment so that the customer can check this solution before something bad will happen. Of course, this creates another step in the process that makes the delivery much longer. And at the end, we don't know that those tests actually work in the production. So not very good solution, and we need to try to push it even back to push it back to the test phase or design phase. Okay, so this is not only the situation that we are facing. Other cases when we are trying to push the feature to the production and we have not finished until the release date. So we have a couple options here. Or we can try to prolong the release and push the deadline forward, or we can try to fix it quickly and or we can try to hide it from the source code and push it without that. But then we are risking that something will go wrong and we will not hide it entirely and break the production. Okay, what else? If we are successful enough, then our product will be used by multiple customers, and which means that we will have multiple versions of our software. And every of this version will have its own set of features, though they will be different. We'll have to manage that. And it's not possible to do without introducing more pipelines, more branches, and more versions of our products, physical versions, yes, as a source code. So then, if we will break something, we'll have to fix all the issues in the multiple products, in the multiple pipelines. Doesn't sound very good. In time, it's getting worse and worse as we grow, as we are getting more complex. Also, this process is becoming more complex and harder to manage. It's getting slow, and the result is not predictable. So what can we do about this? Well, and here comes the feature toggling concept. Let's try to apply this feature toggling to this diagram. First of all, if we have the feature toggles, we can disable failed feature at the production, not affecting other features that were released at the same time. Then we can remove the verification environment, because now we can enable a given feature for isolated amount of people at the production site to test this feature before it will go live. So let's remove it entirely. It's much better. And then what about the incompleted features? So the same mechanism can be used to simply disable features that are not finished, but which means we don't require more pipelines and more copies of our software. Everything is in the same place, which means it's much easier to manage those versions. Now the versions are not physical copies with information about features hidden inside inside different pipelines. Now we have everything in one source code, and we can decide using some kind of a metadata what we will release, what given product will be at the end. And of course, now we just fix bugs once, because they will always happen. So I think it's quite an interesting idea, and maybe it's worth a while to invest and see what those feature toggles are.
Okay, thanks, Piotr. I think if we understand now the potential gain that we have from feature toggling adoption, we can introduce some basic concepts, so we can dive deeper later on and talk about more of those technical challenges that come when we try to introduce feature toggling in our system. So what is the feature toggle? Basically, it corresponds to a feature in our system, and it holds its state, which is usually just binary state, enabled or disabled. As you can see on this simple diagram, if feature is enabled, we run this part of code, and if it's disabled, we act like this feature is not really existent in our system. So this can be shown as a code snippet as well. Here the feature toggle is the use new feature variable, and we check its state, and if it's true, we run the method that executes given feature. And second variant of this is equally viable. You can imagine that we have an old implementation of some algorithm, and we introduce a new implementation, perhaps to increase the performance of the solution. So we use feature toggles to switch between the older and the newer implementation, and for example measure the execution time. And one thing to notice here is that this feature toggle is compile time toggle. So if you want to change the state, we have to comment or uncomment the line and recompile the code. And depending on our use cases, this might not be enough, and usually isn't. So later on, we will try to think what to do to make it this runtime, add this runtime aspect to toggling. And there are many ways how to implement toggle point. There are some two good practices to follow, and a natural progression into extracting the abstraction for toggle check. So you should encapsulate this toggle point from the usual business logic in your code base. So at least a separate method, maybe a class, something like that. And you should make the code, the actual code, or let's say code before toggling, be unaware of any toggling happening in a system. That's just clean. That will make this code still as testable as it was. So now about providing that unified abstraction, let's see it on an example. We start, as I shown you before, with a simple Boolean variable, and we check its state to decide what we'll do, which feature will be executed. And we want to add this runtime aspect to our toggling, so we need to parameterize it. And for example, we take the state from the variable and save it to a file. Now we need, for example, a method that will read this file and return the state for us. And now imagine that we have tens or hundreds of such pieces of code in our code base. It's just a natural, simple thing to do, that we should introduce some kind of abstraction that handles it at this one center point in our system, and it's called feature router. And feature router for now seems like a small class, but actually it can become a module, independent service, or the whole platform pretty much. And now that the router grows bigger, it can make the decision about whether is disabled or enabled, not only using feature state, but it can also use environment type. So depending on which, whether we are on test environment or production environment, we can decide different. We can create user cohorts. So we can, for example, set things up. So one of the features is a premium feature available only for 5% of the users. And this goes on. We can customize it as we wish, according to our needs. We can even define toggle hierarchy, where we model parent-child relationship. If you need it, you're free to do that. And last missing piece in the puzzle is that configuration I briefly mentioned, the place where we extract the toggles. It's usually a file, maybe a database, but we start with simple mapping. As you can see on the left, we have the toggle name and its state. And on the right side, we can see that it can evolve depending on whether you want to manage your toggles, for example. You can then hold also a business readable description, an expiration date, or perhaps an owner field, which might be the team that implements given feature. And putting that all together, we have the client code part, and client, not our client, but client to the router abstraction. This client code just introduces the toggling points. The router API abstraction, the module, it's responsible for evaluating the toggles and defining some custom rules as we wish. And there is a data source that holds the configuration I just mentioned. It can be a file on a file system or database on a central service. Again, this is really customizable. All right, so we have some basic concepts established, and we want to start talking about our story of introducing feature toggling in our project. And we had to face two initial decisions. So before we get to context and technical challenges, we want to tell you about what were the decisions and how we made those. And the first obvious decision we had to make is, should we use feature toggling at all? And this question is more than viable, especially because at least one company failed miserably, and they used feature toggling. I highly encourage you to check this out. We won't tell you the whole story. We have some more important stuff to tell you today. But long story short, they repurposed a 6-year-old toggle for a new feature, and when they toggled that on production, this old code turned out to be malicious or some test code. It basically sent thousands of requests to stock market, and in 45 minutes they lost $460 million, and they had to shut down on the next day. Sounds pretty dangerous, right? Yeah, but they made a lot of other mistakes as well. It was not only about feature toggling, and so we assumed that we won't fail that bad. Yeah, and Piotr, what were the other decision points we had when discussing this question?
Yes, so this sounds very bad, yes. A single mistake can lead to massive fail in the production and actual loss of the business. So we cannot treat this lightly. And besides of that, if we will introduce the feature toggling, then we will accumulate many features in the same source code. So the complexity will grow, and we can do nothing about this. Besides of that, an entire software development process will be affected. So we can expect that there will be many technical challenges and organization challenges for us to overcome. But at the end, the reward for the success is so big that we cannot simply ignore that. So we decided that we should actually try our strength and try to do this and use it. But under one condition, we should minimize all those identified risks and learnings from the others to minimize the risks from the beginning. Yes?
Okay, so we're in, and now second decision, equally important, is whether to use our own solution or choose an external product, perhaps. And an advice to you, I think you should generally start by assuming that there is an existing solution that is applicable to your needs, especially if you have a younger, more flexible project, or if your project is based on cloud architecture using cloud solutions. There's plenty of those, and we have small open source libraries, and we have all-out platforms. We call them toggling as a service, pretty much, enterprise solutions. So there is a lot on the market. Even though there are a lot of solutions, we decided to build our own solution. There are a couple of reasons behind that. We needed a lot of control over the architecture, over the technological decisions. We had that strong requirement to not have any outside dependencies, influences. We didn't want to share any client or R&D data outside to the outside world. And there is one particular reason that was, for me, very interesting as a developer. It turned out to be a great learning opportunity. If you have a solution that requires multi-layer competence development, it might be wise to drive that competence from the bottom. And engineers spending their time building those solutions learn about many technical challenges. So it helps us not end as Knight Capital Group, for example. Okay, and now we are ready to talk about those deeper technical challenges. And Piotr will tell you a bit more about context of our project, because that is pretty important later on.
Yes, so we already saw the risks that we are facing with, but this is not everything. We have decided that this solution and our own solution will allow us to tailor this to our own needs. And what are our needs? In our situation, we are dealing with a mature application that was developed over 10 years or even more. So we have many versions of our product. We have millions lines of code. And some of the teams created simple forms of feature toggling solution. So now, when we are doing our solution, we need to focus on integration problems so that everyone can use it seamlessly. Then the work is, as this product is very big, then the work needs to be distributed. We have multiple teams need to work on this simultaneously and share the same environment, because everything is integrated at the end. So those are the things that we also need to take into account, allowing them to work seamlessly. Besides of that, our application is not simple, it's a big application. So it's a distributed application with multiple instances and applications. And we need to somehow synchronize this and the execution of all those components. And we need to think about how to do this with our feature toggling platform. And at the end, we don't have the luxury to enter the production, which is very often the scenario that is described in other continuous delivery and feature toggling implementations. Our customers have very secure environments that we have limited access to. So our main focus will be to support the development before we ship it to the customer. And of course, then other teams at the customer side can also take advantage on that. So lots of technical challenges, don't seem too easy, but I think we'll manage. Yes, Filip?
Yes, yeah, so let's get right back to the code. We'll start with a challenge that will be most relevant to the programmers who will have to write those toggling points in the system. And I guess a lot of people start when seeing those feature toggle implementations of those if conditions are worried, what about the tight coupling, what about increasing technical depth? And I briefly mentioned some good practices about writing toggle points, but let's get a bit more specific here. So we still have some business logic coupling and business and toggling logic coupling, and the example on the left is usually something that we see in classes that are still related somehow to business logic. And if we follow some basic design patterns or like good design principles, we usually tend to create codes in such form on the right. So we inject the toggled implementation already to our function, our class. And the toggling is happening somewhere else, somewhere before, for example, in a factory class. And there is one additional challenge here. And let's look at it with this example. We inject the correct implementation of an interface that we called logic here. And then we proceed to make some continuous processing in this example in an infinite loop. And we process some data. You might notice that we lost the runtime aspect of toggling now, because if something changes in the configuration, we won't notice it during this processing. So all in all, having all that in mind, our router API should deal with those two challenges to encourage that better design based on some design patterns and dependency injection at the client's code side, but also ensure that client won't lose that runtime aspect of toggling. And there are many ways to handle that. There's no one solution to this challenge. We want to show you one we've used because we stick to pure Java language without using any external libraries and dependency injection containers. Okay, this is the biggest chunk of code you will see at our presentation, so we try to highlight the parts that are most relevant at the moment. The first part is the setup phase. Nothing really interesting here, but just to show you that we've built some basic abstraction. We have the feature class now, and we have that factory that we'll use later on. We pass our basic feature router object and the feature we want to use. And now we have two components, two implementations. In this case, this is some kind of processing of JSON files, and one of the implementation, the new one, consists of some new feature called autocomplete. And what we do now is we use the factory to create a toggled component, as we call it. We pass the type we want to achieve, and we pass those components. And what we receive is the toggled component that has a proxy underneath. So if you look at the usage, on each call of the process method, the toggled component uses proxy underneath to decide whether to use the old implementation or the new implementation, right? So that basically solves the challenge. And as I said, it's not the only solution, but it's the one that worked for us nicely, and we didn't make any couplings to other technologies. Okay, and we arrive to the second challenge. This one is pretty concerning at the beginning, because as we have, as Piotr mentioned, we have some distributed applications. Many of those will use the single component, and we were afraid that we introduce a new single point of failure in our system. And there are two aspects of this challenge. The first one is to give the client's code this freedom of how to handle anything going bad at the router side. And we introduced error modes that can control how router behaves. Basically, using the safe mode, all the exceptions are locked and a default disabled state is returned. This can be useful in critical production environments when we cannot let any exceptions to happen and shown to our client, for example. And the second strategy is the fail-fast strategy, good for development, for first exploration, where we just throw the exception and let the client handle that. And okay, perhaps the more interesting aspect of this challenge is what to do when data source that holds the configuration is not accessible, for example. we started to think about how to solve that, and we actually identified some business use cases. So it's not only about failure here, but we actually want to achieve some additional results by using our data sources. For example, we want different setups of data sources on different environments, or we want a configuration that is just set in stone. It's always there, so we are safe that even in the worst case scenario, we still have that default configuration. So we achieved that using resilient configurations and that backup abstraction. This is on the simple diagram. We can see that if the data source is unavailable or it lost part of the toggle data, we can fall back to the backup data source, so we are safe, and we can configure many of those backups. Looking at the code now, we see an example of how to prepare our router using those backup abstraction. We point to a central service, which is our primary data source, and we then proceed to add backups. First is just some file. We point to a file on the file system that we hope it will be there as well. And if anything goes bad, we also add this backup of just default mappings of feature names and states, so we are safe in the worst case scenario. Okay, 2 challenges solved. What's next in the bug?
Yes, so we now have developers that can easily decouple their work from the toggling problem. And besides of that, there are some other interesting features that actually can help developers in work. Then we actually guarantee that the application will not fail because of our implementation. So now it's time to put this into practice, put this into environment to be used by our applications and by multiple instances of those applications. So it seems that it works. Yes, everyone, every part of the solution is working. But now the developer finished its work, and he wants to check, or she wants to check that the feature that he was working on is completed. The same is with the tester, who would like to check this feature before it's approved and toggled on, and the product manager, product owner. So we need to have some way to synchronize the state of the toggles and change them at the runtime. So as Filip mentioned, we already thought about this in the toggle component that will act as a proxy that provides the fresh information about the toggles. Now we need to centralize the toggle change functionality into some central place, like central toggling service. So when we will do that, we are now facing another multiple challenges. We need to somehow to deliver those toggles to our agents that are residing in the applications. So for now in our solution, we just try to pull it and cache the results. So eventually applications will have the current state, but at the end we would like to have this push mechanism that everyone will be informed. So this is one part of this problem, and then we have the other problem. We need to somehow deliver the toggles to our application so that everyone can see this and use it. So here we are using the same router abstraction and the same backups abstraction to define the source from where we want to get this data. So we can easily use a file, we can use the database or some existing configuration management. Okay, so everything is working, and now it's time to test our application. So if we use this toggle component abstraction, then we created a unit of new functionality, and we can test it in isolation. Toggling is not required in this place. So let's move on and integrate this with a module. So at the module level, it is not so easy because the module can be configured now in a different ways, depending from the feature toggle flags that were set. So now we need to somehow inject the the toggling states that we want to use for tests to that module. So the first solution was to actually provide this possibility to inject those states, and as I remember, we have some interesting testing logic that can be used by tester to make it much easier. And at the end, we have this entire application, and there is no other way than to expose the API to change the feature toggle states for end-to-end tests, to check, for example, all the versions that we want to provide. Are they working? Are all those features are working together as we expected? So this is only the interface that we want to provide, but feature toggling actually creates much more challenges for testers. Yes, now the testers will not have a simple test, but their tests will have to be also toggled, maybe, or they will have to define what toggles need to be used in the production. Also, when the features are depending from one another, and the toggles are depending from one another, it will also cause a challenge for the testers. So those things are yet before us. We hope we'll find a good solution for that. Okay. Now, everything is great. Our application that is mainly in Java is working. But what if we have different components, like in Python or JavaScript, which is also the true, or someone else want to use this solution? So after this isolation of central service, we now can simply communicate with the service over the REST, and we can provide thin clients to the customer side implemented in this specific technology that someone wants to use. So it's important for us not only to provide our solution, but to describe what challenges have we found, create such kind of a blueprint for other implementations, and allow them to connect with our service. So this is our idea for now, how to solve this problem. Okay. And at the end, now everyone is using our solution, want to integrate this library to their own source code. And in some cases it will be straightforward. In some cases it will require a design, because we need to isolate the features that maybe are somehow embedded inside the code, and it's not easy to actually toggle it. And in some cases there will be existing feature toggling implementation. So in these cases we provide open abstraction interfaces to solve this problem. That if you have your own way to provide the toggles, you can simply implement our simple abstraction called reader with a function is enabled, because at the end what is the most important is to provide the information, turn on or turn on, which is a very powerful abstraction, because now we can hide every decision that we have made before we have returned the state, which means if we have an implementation and we have our own specific needs, we can simply extend this interface and define our own rules when given a feature should be turned on. There is also another option. You can cover our API with your simple implementation, but then you will lose the access to our convenient APIs like toggling component, as it works with our component. Okay, so this should be at the end the developers should be able to fix it quite easily, we hope. So let's summarize the challenges that we have faced.
Right, so we've dealt with some challenges across many aspects of software development. We've been deep into the code. We work with testers. I think we can agree that there is always a new challenge when it comes to testing feature toggled systems. We successfully integrated our solution into this distributed multi-language system, and even though we've faced a lot of challenges, we've solved a lot of them, we still have a lot of them on the horizon. And this is, for me, it's really nice about feature toggling is that you can go as deep as you need. You can start with a lot of basics. You don't have to use a lot of those machinery and all those different implementations. But if your needs are more complex, you can add to this solution and build on that another abstractions, another cool mechanisms. And I want to talk about one particular from this unsolved list because it's particularly interesting. What we haven't talked about regarding the technical debt created is the aspect of all those toggles staying in our repository after we release a feature, right? For some scenarios, we probably need that toggle for a week or a month, and we could actually get rid of it. So one of the problem is how to create a toggle cleanup process. You might have remembered that I've shown you this expiration date idea, where you define the date until the toggle works and then switches off, so you have to handle that. But there's some people found another really nice idea, I believe, which is to repurpose those dead toggles into feature counters. So each time we check if feature is enabled, we can assume that it is used in our system. And that's how we can identify unused features, which is pretty agile, if you ask me. And this is just one example, a bit simplified, but what we want to share with you here is that there is a lot of those technicalities that can be done to really tweak that feature toggling solution to your needs. Okay, and we reserved some time for challenges that were not as technical, but for us are equally valuable.
Yes, so first step was to check if we can actually implement something, what technical challenges are behind of that. We've got the positive feedback, which is very good, because then that means we will get the funding, hopefully, for the next phase. Now, what will be most important for us is to introduce this to the organization. This step that is commonly overlooked. Yes, the common scenario is that there is some new methodology. Someone says, "Okay, from today we are using it," and in this case, it will not be as easy. Yes, because we want to minimize some of the risks. In case of major organizations like our, we have multiple roles, major processes, major product, and everything is optimized. So it's not easy to make a change to such a system. Yes. To proceed with that, we need to carefully plan our actions and introduce it step by step, by engaging everyone, and at the end we will have to rebuild many of the processes if we want this to actually work and to be useful for everyone without the risks that we have mentioned. And the first step to implement this was to bring it to the R&D teams in form of a kind of a challenge.
Yes, and I was one of the people who took part of this challenge, and as a developer I was really excited about a bit customized different form of a hackathon, of a usual hackathon. And I think there is a bit of insight here to be shared with you, and maybe you can apply some of those customizations at your organization. So as we mentioned before, feature toggling requires a lot of this technical analysis up front. It's not like a new hot library you can just tell your programmers to use, and it will magically start being used in your project. On a lot of layers, there has to be this competence development, this exploration, and we organized a hackathon that is a bit more calm. The duration was 5 working days instead of, for example, 1. And all the teams were free to continuously get our support from the architects. So it was more of 5-day brainstorming with the architects, and I think it's just a great approach to building that competence from the bottom and not just commanding those new changes from the top and expecting that everything will just fall into place. Yeah, so if you would like to introduce, for example, feature toggling, and your usual hackathon structure might not be fully applicable here, maybe you could try our version.
Yes. Okay, as you can see, we have a very nice logo made in Paintbrush for this purpose. Yes, and of course the results were promising, so we decided to move forward and push it. So we didn't want this to die out, this phase, as the competence were gained, and we started to work to create a project to, with a goal to identify the minimal viable product, the critical parts of the product that we need to have to make another step forward. So we have defined that the most important will be the adapter part that will contain the router providing the API for developers and testers. And it need to be very easily integrated. It need to be, yes, it need to have this property of easy integration to existing solution. Then, because of all those risks and problems that it might cause, we cannot just provide this raw interface that would just check the state of the toggle. We had to implement a convenient API, which and part of that API is toggle components, abstraction, and some other methods to minimize the negative impacts that feature toggling might cause on to our product. And then, of course, the central service as the way to work on the toggled code. So this is our first approach. We have implemented this, and it looked like the first feedback is very positive. So what next? As we said, the process contains of multiple elements. So we now need to face another challenge to provide the proper knowledge to every role in our system, adjust the design, change the composition way we are making, change the software engineering way that we isolate the responsibilities. Yes, our code need to be more single responsibility oriented, and open-closed principle need to be applied also, so that we can easily change them. And then we need to apply this on the coding level, so that it is actually used properly, applied to the test phase. We need to change our continuous integration pipe so that it can use those toggles and bring us the main benefit that we are expecting to have. And at the end, it will change the version management process. Okay, so summarizing.
Right, so I hope we made one thing clear throughout this talk. Feature toggling is not just a small piece of technology you can quickly integrate to your system. It's really powerful. It's customizable, it's flexible, it can be and it's pretty surprising, right? As we shown you some if conditions at the beginning, and it quickly turns out that there's a lot of possibilities on how to expand this solution to something big. Yeah, and I highly encourage you, as I said, to read about Knight Capital Group story, because with great power comes great responsibility, and this is just a consequence of feature toggling being multi-layer subject. It's not happening only in the code, it's not happening in the tests, it's also about our organization, our mindset. So you should identify those risks, be sure about what you really need, and try to tackle all those challenges, exploring all the possibilities, and not just being conscious enough. Just try to be sure before you use toggles, before you, for example, decide that you will create your own solution, right? Try to ask those questions and make sure to not fall into a same trap that some companies did.
Yeah, so and the next key takeaway from this lecture is that as you saw, there are many challenges and they can be effectively controlled. Even if it looks like it cannot be done, in most cases we can do this. Yes, and don't forget that this is not just another library. It can cause several severe damage to our business if not used properly. We need to apply it to all the levels of our software development process, to all the roles, that they understand what is at stake.
Yeah, and that's all. We haven't explored the whole spectrum of feature toggling, but that's the basics and some of our story here to hopefully make you excited about it and read further about feature toggling. And that's all from us.
Thank you.
Thank you for your attention.
And try it.
Yeah.
I hope it will work for you also.
Thank you so much, gentlemen. Thank you very much, Piotr, Pietroń, Filip, Olszewski. Thank you so much for your in-depth analyses. This is Code Dive. We're broadcasting from Nokia Garage here in Wrocław, Poland. Stay tuned for yet another presentation today. Our speaker now is Xavier Bonaventura, and Xavier is a software engineer at BMW, where he works on the software stack for the next generation of autonomous driving, including the coordination between the software quality and the software development team. He believes that success in large-scale projects can only be achieved with high-quality standards, modern technology, and applying software engineering principles at all levels. His areas of expertise are computer graphics, information theory, and also data aggregation with code bases of different sizes, with contributions from 5 to 2,000 software developers. He loves learning and teaching, and when he's not programming, he likes cooking, hiking, and jogging. Xavier, over to you.
Hello to everyone. My name is Xavier Bonaventura. I'm from the BMW group, and today I'm here to give you an introduction to Bazel to build C++ and Python. A little bit about me. I'm a software developer at the BMW since 2018, and I'm working at the Department of Full Autonomous Driving. I've been working with Bazel for around 2 years since I started BMW, and mainly I work on C++ and Python as programming languages. Let's start first about Bazel. What is Bazel? Bazel is a build system. It's not a build generator, like could be CMake, for example. It invokes directly the compiler. It provides full functionality for testing. It can give you test reports. It handles flaky tests, and a lot of other functionalities. And mainly it's written in Java, some small parts in C++, and then has some rules and macros that can be written to extend Bazel, that these are written in Starlar. For the history, we need to first go back to Blaze. Blaze is the build system at Google. Development started around 2007, and part of Blaze was open source on 2015. With the name of Bazel. And it moved from beta to general availability more or less 1 year ago, in October 2019. The release process that it follows, since it's general availability, it follows semantic versioning, and they skip a time span of minimum 3 months between major releases. And they provide a minor release every month based on GitHub help. This was until now, but now in next month, starting with Bazel 4, they provide long-term support, similar to what we can find in Ubuntu, and there will be major releases every 9 months. And in this long-term support, they will provide support for around 2 years. Let's go a bit over the Bazel features. The main feature for Bazel is fast and correct. And basically this allows incremental builds, test execution, also incremental test. It provides parallel execution. It provides a local and remote cache. And basically also has hermetic builds thanks to sandboxing. It's multi-language and multi-platform. It supports a lot of different languages, Java, C, C++, Android, iOS, and the ones that are not supported can be perfectly added. It runs in multiple platforms, Linux, Windows, macOS, and it can also run in some other platforms that are not officially supported, but it can be compiled because it's just Java. It's scalable. It's intended to handle code bases of any size. This is coming from Google. They have a huge monorepo, and it can handle smaller repos, but it can also handle multiple repositories. It's extensible, and to extend it, you can add a platform, you can add a language if it's not supported, and basically it uses this Skylark language that is similar to Python. Okay, now what's Bazel in a nutshell? It's an artifact-based system, and We have inputs, we have actions, and we have outputs. The inputs are treated as artifacts, the outputs are treated as artifacts, and the actions are treated as artifacts as well. And for every artifact, we can compute a hash in advance. With this way, we can use caching. Thanks to the we search on the cache with this hash, and if it's available, then we don't need to build the artifact. Each action runs on a sandbox. With this way, it improves reproducibility, and you can better detect if you have some dependencies and declare, and you don't have the issue that you are pulling in the dependencies when they were not even declared. It's composable also. It means that the outputs of an action can be used as inputs of another action, and an action can be the output of another action. Okay, let's go a bit on the design to understand also a little bit how this speed comes from. Bazel follows a client-server architecture design. We have a Bazel server and we have Bazel client. And the first time that the Bazel command is executed, a server is started on the same machine. After the Bazel command finishes, the server keeps running on the background for a certain amount of time. And then the following command that is executed uses this already running server. There's one small thing, two clients, they cannot run in parallel. But basically the advantage is that, this architecture allows the server to cache information between commands execution. And the Bazel server can be stopped with Bazel shutdown if you want after running the command. Then the basic files from Bazel, we have mainly three types of files. The first one would be the workspace. This file is unique. It's at the root of the source code that you want to build, and it can be empty, and it's used to declare external dependencies mainly. And where this workspace, the folder where this workspace is located, it would be our repository. Then we have the build files. These are the files where we will define the targets. It's at the root of a package. And a package is defined by all files, folders, and subfolders at the same level like the build file, except these folders that already contain a build file. And with this way, you can have, like you see on the right, this package and subpackage structure. And then in addition, we said that Bazel is extensible, and basically we have these BZL files that are used to define Bazel extensions, and they can be loaded in a build or in the workspace file using a load statement. To reference to all of these packages and targets, Bazel uses labels, and a label in Bazel looks similar to this that you are seeing. There's a repository name, and then you put the folder, subfolder, until the build file, and then colon, and then the target name inside the build file. You can omit part of this label. If you omit the repository, it assumes that you are in the current repository. You can also omit the part after the colon, and then it will assume that your target name is called like the folder that contains the build file. And in case that you are inside the same build file, you can omit everything in front of the colon to reference to a target inside the same build file. Let's see now an example for the Bazel labels. Here we have this client server, and now let's imagine that in this client we have the build file, and we define two libraries, small client and a client. Basically, we could reference to this small client target with @example, that is the name of our repository, -- client, this is the folder where we have the build file where the target is defined. and then colon, and then the name of the target, that is small client. In this case, we could omit example, and this would still be okay. And then for the other target for client, we have the same option, but in this case, because the target is exactly named like the folder that contains the build file, you can also omit everything that comes after the colon. And in case that you are in the same build file, this build file inside client, you could reference to client and small client, just colon and name of the target. Okay, another concept that we have in Bazel is target visibility. And basically, when we define a target, we can also define who can see this target. This we will do it with this parameter called visibility. This will be a list, following similar to the Python style for defining list. And basically, we have several values that we can put there. One would be / visibility private. This to indicate that it's only visible inside the same build file. No one outside can see this target. We can also define that the target is public, just same principle, but ending it with public, and then anyone can see this target. For these two cases, you are not allowed to define multiple visibilities in the list if you use private or public. Then in addition, we can also say that the target is visible by a specific package and all of its sub-packages. And basically what you do, you follow the similar like for the labels that we saw before, but instead of putting the name of the target, you just stop at the build file and you say sub-packages. And then you can also say that it's only visible for a specific package, but not the sub-packages. And this you can do it with _ package. The visibility can be defined per package, per target, or both. If we don't define it per target, it by default is the same like the package. And if it's also not defined, then it's basically private and it's only visible within the build file. And this is most of the targets how most of the time will be. Now let's move to the phases of a build in Bazel. Bazel is the structure in 3 phases. We have one that is the loading phase. In this loading phase, it's the part of loading the files, loading the extensions. It's more like the physical process of loading the file system that is relevant for your build. This is a phase that takes several seconds the first time and then can be cached. We have the second phase, that is the analysis phase. And now here we have everything loaded, but now we start doing some semantic analysis of each rule. We build a dependency graph, we see that everything is correct, and we analyze also that what work needs to be done. This is also a phase that is quite fast and also can be cached. And then finally we have the execution phase, where the targets are built, compilation, linking, you execute targets, you run test, and this is where you will spend most of the time. But also part of this can be speed up thanks also to caching. Okay, we talk a lot about Bazel cache. Let's now see the different levels of cache that we have in Bazel. And we could say that we have 4 different levels of cache. The first one would be in-memory cache. It's this Bazel server that we saw, this cache that goes across Bazel executions, and it's clean or lost every time that the server is stopped. We have output directory. This Bazel out is a directory that will be created at the same level like the workspace file. It's local to the workspace, and you can also remove it with Bazel clean or Bazel clean expunge. Then we have the disk cache. This is a folder in the local machine. It's useful to share artifacts when you switch branches, if you have your repository check out multiple times in the same machine. And the only thing that can happen is that it can grow quite a lot, and one recommendation is just to clean it from time to time. Then in addition, Bazel provides some protocol for remote caching, and basically you can enable remote cache. It's nothing else than an HTTP server, and it's useful to share artifacts between team members or with the CI, that if someone else already built it, you don't have to build it. Bazel cache is always valid and correct, and you should not clean it. In general, you should never clean it. The only reason why you should clean it is to get some free space. If at some point you solve a problem doing a Bazel clean, a bad ticket should be created. This is an issue. Something went wrong. It might be on the Bazel core, it might be on some of the Bazel rules, or it might be in one of your toolchain configurations, or some of the Bazel extensions that you created. If these are from the Bazel core or the Bazel rules, usually these bugs are taken quite seriously, because it's something that is the fundamentals of Bazel, that we have a proper cache mechanism. Bazel local cache setup could look something like that. We have the several workspaces checked out. In each workspace you have this Bazel out folder, and then in addition you have some folder inside that is this cache that you can share between workspaces. When we see this in a higher level, we can see, like with remote cache, this is one of the setups recommended by Bazel. We have the different machines that are reading from the remote cache, and we have one CI machine that is reading and writing to the remote cache. The reason is why you have only one machine writing to the cache is to have a little bit more control. Usually the CI machine, you have quite control on it, but on the developer's machine, it could be that you have not so much control. Maybe some of the parts are not hermetic, and you could corrupt the cache. With this way, you just leave it to only one machine writing to the cache. You could go to a more distributed approach. You could have several remote caches, because if you have one single remote cache, you will start having problems of bottleneck to access, to read, write the cache, and basically you will start needing to do some balancing or replication. And then the other option that you have is just, you can create several remote caches, and then you can have some, let's call it cache heater, that is a single machine that takes care of warming up this cache. Another feature that we set is like, it's remote execution. It's like, because we said that the idea of Bazel is that it's also very fast, and how to make this fast is through remote execution. Bazel compilation and execution can run in different machines. We would have the most simple scenario that Bazel executes on one machine, code compiles also on the same machine, and it's executed in the same machine. Then we have a second scenario that the execution, the compilation happens in a single machine, and then the code execution happens in separate machines. And then we could have the third scenario that we have compilation in different machines, execution in different machines, and we have Bazel execution on a machine that the only thing that it does is just orchestrating all of this. And you could be compiling your code in data centers, executing the test in data centers, and with this way speed up really a lot. Okay, now let's see an example of Bazel for C++ and Python. We said that Bazel is extensible. Bazel supports multiple languages. We already saw a little bit how it looks, the library, but let's go deep into that. The first thing that we have to do if we want to use C++, we need to load the C++ rules. We have binaries, libraries, and tests. These are the three types of rules that each language implements. And then we have the same for Python. And then we will have the three most basic commands would be Bazel run to run a binary, and then build for building and test for testing. Straightforward names. And when you run these commands, you can always use wildcards. If you use wildcards, basically you are building or testing all the targets that are under these wildcards. Okay, but we set a build system for Python. Why? I mean, Python is not compiled. I mean, why would you need it? C++ is a compiled language. Okay, it's normal. We need a build system. But Python is an interpreted language. Why would we want to use a build system? Well, if you use a build system that to control also your dependencies, then it's more difficult to leak dependencies with the sandboxing. You have a unified way in Bazel to run your targets across languages. You saw Bazel build, Bazel test. You don't care which language is being run. And you have the benefit of a lot of Bazel test utilities that Bazel provides that we will see later on. And of course, like for Python, it doesn't make sense to build something, but still you need all the rest. Let's see how it looks a C++ example. We define here, we call the load, loading the binary and the library. And then we define this CC binary, and we have this parameter name. This is common to all the targets, and here it's to specify the target name. Then we have the sources, that these are the files needed to build your binary, and then you have the dependencies to say on what you are depending. And here you would define your libraries. For a library, we have a similar approach, name for the target, and then here the sources and the headers. The sources would be everything, all translation units of the library, and the private headers. And then in headers, you would put only the public headers. With this way, you can keep a clear separation between public and private headers. And then to run this hello world example, you would just call Bazel run, and the label of the target, if it's in the root, colon hello world. In case that you want to build it, you do Bazel build and hello world. In this case, would also take care of building the library because it's needed to build the hello world. And if you just want to build the library, then Bazel build and the library. We have also these targets for testing. This would be a CC test. And basically you have the sources also, that it's the sources of your test, and then you have the dependencies. And for the dependencies, it's the same. You say on which libraries you depend. When you run it, you would call Bazel test and the target, and then you would see a summary of the test, if it passed or not. Now let's see on Python. On Python, it looks very similar to what we just saw. You load the Python rules with the statement, similar like before. And then here we can define our PyBinary and PyLibrary. And it's important here, the differentiation between binary and library, because a binary can be executed and a library cannot be executed. But it's the same. Then we can run Bazel bin, Bazel run, and the binary, Bazel build. And in this case, it will happen nothing. It's Python. It will tell you nothing to build. And if you would try to run the library, it would tell you that this is not an executable. And indeed, you would get the same message if you would do it in C++. For a test, as you see, it would look more or less the same. And this would be go on with all the different languages. Most of the rules, they follow this convention that you just put the language underscore library, language underscore test or underscore binary, and you run them with this command. And here is where you see that it's quite handy that it's a unified way for all the languages. You don't care in which language you are programming and if you have mixed languages. Okay, now let's see how Bazel would help us, or like how we would do it in Bazel if we would want to combine Python and C++. Bazel, as we said, can be extended and can be extended in two ways, in macros or with rules. And we have an example that we have an input txt file. We would have a Python executable that basically converts this txt file in a generated CPP, and then we want to compile the CPP and get an executable. Basically what we will be doing is a kind of a customized auto-generated hello world. You give an input txt, it will generate a hello world with this string, compile it, run it, and you will get a different output, depends on the input that you provide. Okay, to do that, let's see which parts we need to do. First, we need to define this generator. The generator, in this case, we want to do it in Python. Then basically we have a Python program that it takes a file path as an input, another file path as an output. And basically what it does is to generate a CPP file that contains a hello world, that it says hello, and the message is the one that comes from the input file. This generator, we define it also in Bazel, like we saw that we define any Py binary. We put the name, we put the sources, and we can set here the visibility flag to public because this will need to be visible. Okay, now we have the generator. Now we can put a macro around it. And Bazel, there is some native rules, and one of the native rules is this gen rule. And basically now what we do is we define a macro that is called hello world, and you just give a name, a target name. And basically what we'll do, it will instantiate this target gen rule, that the name will be the same name that you specified, and then as the sources will be the name that you put .txt, the output will be this name .cpp, and here you can pass the command that will be executed. And here you use this location to indicate wherever that is, and you can put the label of the target. And then you have this special syntax with the dollars that basically it expands to the sources and to the outputs. And here you have these parameter tools that basically it's to say kind of like your tool dependencies, like which tool is needed to run this rule. And we are referencing the generator that we saw before. And here we put the visibility that depends on how it was passed. And then now the only part missing would be to invoke these macros. On a build file, we would load the macro that we define, this hello world, and then you can just define it like that. Hello world, you put the name, in this case, yeah, code dive, and one that's called everyone. And if we remember how we define the macro, this will search for codedive.txt when you try to run it, and everyone.txt will generate a CPP. And then if we see, we define this CC binary, that what it takes is as a source is this hello world code dive. And this is the the source will expand to this generated file. And then basically we can run it and we'll get the strings that we just saw. Okay, but let's wait a second. We said that if it's Bazel, it's hermetic, everything is so hermetic, but now the question comes, why we did not have to specify our compiler? Well, for practical reasons, Bazel provides some predefined toolchains. A toolchain is nothing else than the definition of all of your tools that need to be used for your language. In C++ would be the compiler, compiler options, the linker, etc. In Python, you could have the Python interpreter, the Python standard library, etc. And Bazel provides some predefined toolchains, and if detects that you have some compilers, they can be used automatically. When you run a Bazel command, you can use this toolchain resolution debug, and you can see which toolchain has been selected. Still, if you use Bazel for any production project, you should be defining an hermetic toolchain. Defining a toolchain is not enough, because you could define a toolchain that points to some local compiler installed. But this can bring to one person is using a version, another person is using another one. And basically compilers and linkers should be provided like an input artifact. This should be checked in, with this way everyone is using the same compiler. And the Python interpreter the same, should be an input artifact, with this way everyone uses the same Python version, independent on what you have installed on your machine. As a general rule, if a user needs to install something in his machine apart from Bazel, then you are doing something wrong. And you should revisit that. Bazel provides a lot of documentations on how to define toolchains, and you have also some tutorials that you can check. Okay, one thing that we said is quite important on Bazel is the test runner, the whole test execution engine. We need to remind that all testing infrastructure provided by Bazel is language agnostic. And when you are using the Bazel test, --, it will run all rules that are of type test. It doesn't matter if they are C++, Python, Go, any other languages. It will run all the tests, and except that you can define also in the rules, you can define a parameter called tag, and if you put manual, then it's a kind of deactivate the test or say, hey, this test needs to be explicitly run. And they will be ignored if you run it with the wildcards. The ones with flaky flag set to true, you also have this parameter flaky that you can set to true. This to indicate that the test is flaky, and Bazel will take care of running it automatically, again, in case that it would fail. Because it considers that it's flaky, let's run it again. It will run it 3 times to make sure that if it's really failing or was just flaky. Test also can time out. If a test takes too long to execute, then you have also 2 parameters that you can play with, timeout and size. And depends on this combination, this will decide a timeout. And if the test takes too long, then it will just be stopped and failed with a timeout message. As we said, tests will run in parallel, but you have also the option in tags to specify a tag that's called exclusive. And what does it mean is that for whatever reason that you have in your test, this test should not be executed together with any other test. This is something that you should avoid, because if you start using it, then yeah, you lose the whole parallelization. The output of the test is always stored to a file, but it will also be displayed to a console in case that a test fails. The output can be shown interactively. If you specify test output stream, then you will see it, the output at the same time that the test is being executed. But you need to keep in mind that if you pass this option, then the test doesn't run in parallel. This is something that you can do it if you are debugging some specific test. With this way, you don't have to go all the time and check the log. Also, in addition, one thing that Bazel provides is that for every target, you can set a parameter that it's called test only. And if you set it, it means that this library can only be used by test only targets, meaning test or other libraries that are marked as test only. With this way, what you are avoiding is that accidentally some testing library ends up in your target, because as soon as you try to have a normal binary depend on a test only library, then Bazel will complain and will just fail. And if a test or its dependencies did not change, basically it's like there's no reason to run a test if nothing changed. You run it once, you know that it passed, you don't change anything, you run it again, hey, it should pass. Then basically in this case, Bazel will cache the result of the test and will not run the test. But when it displays the summary, you will see that it's being cached. You also have an option to use to force Bazel to rerun it. And in the end, after running all the tests independent of the languages, you will have a list with all the execution like you see here on the screen, and basically it can show you like different possibilities. Here we have, I think I didn't forget any. We have a test that passed but was cached, some that are passed, flaky, failed. If the test fails to build, for example in case of C++, you would also see it here, or if it timed out. And in the terms that when they are failing, here they are printing you the log path, and you can go there and just check what was the issue. And in most of the IDEs, you can just control-click to the link, and it will open the log file. Okay, Bazel provides also another command that is called Bazel coverage, and basically it's intended for computing the code coverage. It's relatively straightforward to run. It's just Bazel coverage and the name of the test that you want to run and calculate the coverage. Or you can also use wildcards here and run a lot of tests and measure the coverage for all the tests. And yeah, all of this will collect the information, will generate a that file in case of GCC, and then afterwards you can run, for example, gen HTML, and you can have a report. The issue here is that, unfortunately, Bazel, the code coverage in Bazel is not really complete at the moment. And for example, if we have here on the screen this example, that we have two libraries, foo and bar, and main depends on both of them. This main file, main binary is the one that you want to deploy, it's your production main file. Then you have some test targets like this foo test. If you would run all your tests, you would create the code coverage report, and here you would get 80% code coverage, and you would see that the only file that appears is the foo.cpp that is part of the foo library. The problem here is that you don't see anywhere in this coverage report your bar library mention or your main binary mention here. And this is because to do that you would have to compute the baseline coverage, and the moment that you build the main, you would have to calculate this coverage. But this is not supported out of the box, and yeah, there are some issues for Another cool functionality that Bazel provides, that this helps you a lot to get a lot of insight on what's going on, it's Bazel query. It provides, there are 3 commands, and this helps you to understand the build graph. These are Bazel query, cquery, and aquery. The first 2 are for checking going over the build graph and checking the dependencies, and the query is mainly for introspecting the actions that we saw before. The main difference between query and cquery is that query is running after the loading phase and cquery is running after the analysis phase. And basically cquery considers some configuration flags. But yeah, if you want to know more, there's also the link for the query and you can check more there. But basically how it would work, let's imagine here this dependency graph that we have on the right, like we saw before. And here you would say Bazel query, depths, this to say dependencies of this target foo test. And then you say, okay, you have these 2 parameters, no tool depths, no implicit depths. That is to say, yeah, I don't want the dependencies that are from tooling like compilers or implicit dependencies from some rules. And basically what it tells you, it's like a full list of everything that foo test depends on. Okay, this catch library, foo test cpp.h, etc. This general will be quite a huge list, but then if you see some strange dependency here that you don't know where it's coming from, then you also have some functionality that's some path. For example, here, I want to know how foo test depends on foo.h. Why this dependency? And basically, when you do Bazel query some path between foo test and foo.h, it will tell you, well, foo test depends on foo library, and foo library depends on foo.h. And here is you can see your dependency path. If you do it for another, for example, here, how foo test depends on bar, in case that you would not have any path, it would just give you this info, empty results, there are no dependencies. And this could also be used if you want to make sure that some library does never end up in your production or stuff like that. Okay, we saw that Bazel is just not just building, it comes with a lot of functionalities and tooling. And one of the toolings that is provided also is Baselisk. Baselisk is really quite handy. It's nothing else than a Bazel launcher. But why it's so useful? It allows to use multiple Bazel versions in one machine or in one workspace. You don't have to care about installing it, different versions of Bazel. You just use Baselisk. And basically, the developer doesn't need to care about upgrading Bazel because Baselisk will take the latest one. Let's see, how can be used? You have several ways. One way would be you can define an environment variable called use Bazel version, and you specify the version that wants to be used. And then you can also have a Bazel RC file checked in your repository next to your workspace file. And you put there the version of Bazel that should be used. Or if you don't define any of this, basically Baselisk what we'll do is we'll just grab the latest Bazel release. And with this way, the developers, they don't have to care which Bazel version is used in your project. And it can be run like Bazel. You just do Baselisk run hello world, for example. You can pass all the parameters the same like Bazel, it's just forwarding them. You can also put it into your binary path, rename like Bazel. With this way, you just can call Bazel run, but in reality it's running Baselisk. And Baselisk will take care of, before running, checking the Bazel version, downloading the Bazel version that you need, and running that Bazel version. And you don't have to care anymore about versioning. In addition, one of the functionalities that provides Basilisk is for migration. When you want to update your code to a newer Bazel version, Bazel, they provide incompatibility flags. It's a way that you can test in advance if your code will be okay in a newer version. And basically you can run Basilisk with strict or migrate, and this will check with these incompatible flags, and this can help on the migration process. Then another topic that I just wanted to open is to have some ideas for the future. Basically, Bazel provides also aspects. Aspects is something that allows you, once you have a dependency graph, it allows to augmentate this dependency graph with additional information. You can have on all of your targets some additional information that it's customized, that you decided what it is. And the question here would be for what could be used. And indeed, it can be used for quite a lot of stuff, and I'm willing to see more. One of the main ones is for ID integration. You have Bazel integration in Visual Studio Code. You have it also on Sea Lion and in some others, I think. And basically, this is done thanks to these aspects. You can also use aspects to do static analysis, to store static analysis results per target. You could also use it for code coverage. Some people are using it. Compiler warnings is just another level of extensibility that provides that you can just kind of build a parallel dependency graph that it's binded to the original one, and here you can just run your imagination and decide. Okay, last but not least, let's check a bit the commands. We saw some of the main commands. We still have some Bazel help that you can run it with Bazel help and the specific command. If you have, it's really complete. I really recommend it. You have also some verbose versions. You have Bazel version that is getting especially important if you are using Basilisk, because you never know which one you are using. With this way, you can always call Bazel version and you will check. And then if you want to check documentation, the first thing that you should do is to run Bazel version. You have Bazel build that is what we saw before, and maybe the key functionality here is that you can run only the loading and analysis phase, and this can help you to keep your graph correct all the time. Bazel run, we already saw it also. Bazel test, also saw the coverage. As we said, really not a lot of support for a lot of languages. Hopefully we'll get better. And then we have the three commands that we set for querying. And the Bazel clean that, yeah, remember that if you have to run it, there's some bug somewhere. I also added here some references. There's a talk from Lukáš and Julio at CBBcast talking about Bazel. It's really interesting. If you want to know more about also on what we are doing on the BMW group and how we migrated to Bazel, Patrick and Axel were giving a nice talk on the BazelCon last year. And then if you are interested on Bazel coverage, even though unfortunately it's not so well supported, I strongly recommend this talk from Irina Iancu to really understand all the concepts be inside coverage. And yeah, basically that's all. I hope that you like it. If you want to start with Bazel right away, what should you do? What would be the recommendation? The first thing is that probably like next month will come Bazel 4 in a long-term support. I think it's a nice place to start with a kind of a stable version. Then check the Bazel page. The documentation is very complete there. You have examples. And if you move to Bazel or not, basically the main point here would be, do you plan to end up with more than one language in your repository? And if that's the case, then yeah, it's quite worth it. If you are on Windows, I think unfortunately that the Windows support for Bazel is not so nice like we would like, but it's going there. But yeah, just give it a try. Try with some small examples, and then you can evaluate. There are a lot of things that they reported speed ups like 10 times faster, and the thing is that also we saw a lot of times that it's really correct. That there are rarely times that you need to run a Bazel clean because something didn't work. I hope you enjoyed, and if you have any questions, just write them down or just ask them right away or just contact me later. Thanks a lot.
Xavier Bonaventura on C++ and Python. Thank you very much indeed. So this is it for this year's Code Dive. I'd like to thank the speakers, I'd like to thank our partners, and I'd like to thank our organizers here at Nokia. So Adam Badura, Marcin Wolniak, thank you very much for making it happen. Special thanks goes to Event Stream Company. Thank you very much for recording us. The crew here have been working around the clock. And of course, and most of all, I'd like to thank you, the audience, our participants. It was great of you to join. And I think, yes, this is it. It was number 7 when it comes to Code Dive, and it was the first time we've done it exclusively online. And I'm not sure if I can, but I will share a rumor that the word on the street is we will be meeting again next year for Code Dive, so do join us again. Other than that, my name is Rafał Motriuk. I'm a science and technology journalist. Thank you very much for having me, and I hope to see you before too long.